everybody. He's trying to hand you something, Lance. Cheese. And our teacher.
Okay. Welcome to AC Circuits. Here we go. Things you need. First of all, you need a multimeter. If you don't have one, I got a box of them right here. In a minute, we'll break for a few minutes. You can come get a multimeter if you don't have one. Oops. Oh, it's in my pocket. I hadn't got to that yet. Okay. We'll do a lot of different things this morning. There's going to be a lot of moving pieces, so we're going to be moving around some, passing some stuff down. Jerry and a couple of guys were gracious to put all the stuff on the table ahead of time. Hopefully we got everything out there you'll need for the initial thrust, but then there'll be a couple more things along the way. So we'll make it happen. It'll all work out. We'll make it go. All righty. AC Circuits. A little different from, whoops. There we go. A little bit different from DC in some ways, but yet very similar, just add a little complexity to it. That's kind of what it boils down to. So with that, let's jump in there. What are we going to do with all this stuff? Well, hopefully by the time we get out of here today, you'll be more comfortable with AC. You'll have a little bit more idea about resonance and some of those crazy terms that we use that relate to AC and components and antennas and feed lines and all that good stuff. You have a number of handouts that are there. There'll be one variation to the handout, and we'll deal with that when we get to it. The little breadboard that you have, that's that little thing there that's got all those little holes in it. We'll talk about that in a second. An RCL meter, resistance, capacitance, and inductance meter. I've got several of those up here, and I don't have enough for everybody to have your own. We'll kind of spread them out where you can play with that and play with component values when we get there. We'll talk about the O-scopes. We have 4 O-scopes set up over there. I know Lewis has his, Ron has his, and I've got another one or two up here, plus a handheld. So we've got scopes. We'll have to share a little bit, but I think we'll be okay with that. Frequency counter, we'll deal with counting some of this stuff as we go along, see what the frequencies are and so forth. We'll use a signal generator, which will generate a signal, an AC signal for us in several different fashions, and we'll like it. And we always like to say, we want to do a project at some point along the way. If we do, that's always an open subject. With that, let's talk about the breadboard. I did add a little bit of verbiage to this slide from what we did in DC circuits. In that, if you look at the little, let her get settled there with her outlets. There you go. Good shot. We good? Okay. Okay. Whoops. Uh-oh. Okay, there we go. I thought we lost it there for a second. We're okay. All right, back to the breadboard. There we go. Okay, remember this little guy. Now, some of you have one like this that has the stripes down the side. Some of you have the ones without the stripes, but they work the same way. The ones with the stripes just has more opportunities to make mistakes. I mean, more opportunities for hooking up things. The way these things work is this row of pins next to the red line, or if you don't have the red line, you can pretend there's a red line down there. It's there, you just can't see it. Anyway, all of those pins in those little holes are connected together. Likewise, on the blue line, all of those down beside that blue line are connected together. And the same thing on the other side. Then the little pins across, you'll notice there's 5 little holes there for plugging things in. Those 5 are hooked to each other. They're insulated from any of the others, including the rails on the side. So what we normally do when we're hooking something up is we'll hook our positive battery or whatever's positive to one of these rails and the negative to the blue rail on the other side. Or if you don't have the rails, the outside and the outside. Just remember which is positive, which is negative. So then if I wanted to connect something from this row over to this row, I would have to put a jumper in between those 2 rows to connect those 2 rows together. There was a little bit of confusion on that last time, so that's why I wanted to talk about that just a little bit. And that's, of course, what the verbiage all says. Any questions on that? Are you okay with that? Okay. O-scopes. Let's talk a little about O-scopes. This is where the plot starts to thicken a little bit. On an oscilloscope, we basically get a good depiction of what an AC waveform is going to look like. There are 5 main controls that you need with an O-scope. The first one is the voltage control. The voltage control controls how much that little square between that line and that line, how much voltage that represents. On that particular one, I said at 0.2 of a volt, so it's 0.2 of a volt from there to there. So if I want to know the value from there all the way down to here, I'd have to add up all those little squares and come up with voltage value for that waveform. Likewise, the frequency going across is called the time base, or the time oscillator, and we would set that for whatever time we need to make a good display, get a good solid signal on it. So between those two, we juggle it and we get it where it looks right. Whoops. That scared me. Thought I did something wrong. Anyway, those are two of the controls. A couple of other controls that are key is the vertical control, up, down. With that control, you can actually move this trace up and down. Why would you want to do that? Well, like this waveform here is in the middle of a square. Move it up where it's right at the edge of the square. Then you go 1, 2, 3, 4, 5. Makes it easier to count the squares for measuring voltage. The same thing then will be true with the horizontal adjustment. You can move this back and forth. So you move this, say, maybe to that point right there over here. And so you go from that point to get one full cycle of that wave on the screen to make it easy to measure. And then you would count 0.2 of a microsecond, 0.4, and so forth, whatever the time base is set for. And the last control is one that can be the most contrary of all of them, and that's the sync control, to make this thing stabilized, to get it in sync with the system. Normally the oscilloscope is going to look at the incoming signal and figure out what it needs to sync up to give you a solid trace. If it's not in sync, then you remember the old TVs, how they used to roll? It'll look kind of like that, only it'll be rolling left to right. And so you adjust a little sync adjustment back and forth to get the thing to stabilize. And you'll see that over there on the scopes when we get to that. Questions about that? How many of you have ever used a scope before? Okay, all right. Good deal. Be something new for us. Come on. I just lost it. I'm not going forward. I got that. There we go. Oops. Then it took all of them at once. Okay, next thing. Frequency counter. Basically, the frequency counter is going to count the frequency of an applied signal. And it's going to say your signal is 10 megahertz or 1 megahertz or 200 kilohertz or whatever it happens to be. You remember that metric sheet that we handed out in DC? That I should have printed some more of those off, I guess, because it kind of comes out handy when we go back and forth between kilohertz and megahertz. And we go from microfarads to nanofarads to picofarads and all those crazy things. You have to kind of be aware of the metric system. But at any rate, this particular one that in the picture there is a 2.7 gigahertz frequency counter, which means you can put a signal into its input, whichever one is the input from here, channel one, and measure up to 2.7 gigahertz, which is pretty fast signal. And it'll just basically give you a readout and tell you what it is. Now, all of these instruments, by the way, can be calibrated so that they're accurate. But you have to have a standard by which to calibrate them before you can do that. In my case, for the frequency, I'm very fortunate. I have a cesium beam standard, which is good to 10 to the minus 13. That's accurate. That's very, very accurate. Generates a 10 megahertz signal, square wave signal, and I use that to calibrate my frequency counter. But that's one of the few things. I don't have a calibrated voltage standard or some of those other things that would be nice to have. But anyway, that's the frequency counter. We'll play with that just a little bit along the way. And then the RCL meter, resistance, capacitance, inductance meter, is basically just a meter for measuring the value of components. Most of these RCL, as it indicates, means that it'll measure a resistor, it'll measure a capacitor, or it'll measure an inductor. The glitchy thing comes in is what range will it handle? A lot of the cheaper ones, by cheaper I mean $50 and less, can be pretty iffy. They have a pretty wide span of what they'll actually measure and how accurate they'll actually be on the thing. They won't be all very accurate. And generally speaking, the inductance scale will be the worst. That's where you'll see the worst variation between instruments. Capacitance usually is pretty good. A lot of voltmeters now have a capacitance scale on them as well, which you can use if you want. But anyway, the idea behind it is you hook up to a resistor, set it for whatever resistance scale you need, you get a readout of the resistance or the capacitance or the inductance, whatever it is that you're trying to read. My favorite is this little guy. This little guy right now is $119 on Amazon. Unfortunately, I only have one. I wish I had one for everybody, but I don't. But this thing is absolutely marvelous. How they do this, I don't know, and I don't really care. But you basically just hook it across the component, press the start button, wait 5 seconds, and it says, this is an inductor. It has 4.7 microhenries of inductance. This is a resistor. It's 1.2K. This is a capacitor. It has 0.1 nanofarad or whatever. I mean, it just works, and it's great, and it's very accurate, it's very consistent, and it's very repeatable. So I kind of use that as my standard when I'm evaluating the other instruments. It's now past tense, I guess, a B&K, the next model up from this was made by B&K. And for whatever reason, it just gave up the ghost when I pulled it out of the mothballs this time. Never could get the display to come back up on it. But at any rate, I bought another one from Amazon, of course, Chinese made, $35. That tells you something right off. Okay. And actually the resistance and the capacitance on it is pretty consistent. The inductance is out in left field. This guy says the inductance is 170 microhenries. It says it's 10 microhenries. I mean, it's just way out there like that. And that's kind of typical, really. It really is. But do you need all of that? No, not really for most things. Now, if you're in a critical situation where you need those critical values, you're doing repair work or something like that, that's critical, sure, then it becomes important. In that case, then you invest in a really good meter and pay a couple $300 for it, which will give you much better accuracy for that. We've got several of those. We'll play with those when we come to it. And then a signal generator. This guy does just the opposite of the frequency counter. It generates a signal that you can look at. I have a couple of those set up over there with the scopes that we'll play with here in a little bit, and you can actually see how those things work. Okay, that's kind of the intro to the items that we're going to be dealing with. What is AC electricity anyway? AC stands for alternating current. What does that mean? Basically, it means instead of DC, which is the flat line, AC starts out as a zero line, goes positive a ways, drops down back to zero again, goes negative for an equal distance normally, and back up to the zero line again, alternating back and forth, back and forth, back and forth. Why do we need AC? Why can't we just do everything with DC? More efficient in many ways for what we do. For example, the power when we plug into our so-called 110 volt outlet on the wall is AC. Where do we get that AC from? It comes from a generator somewhere. That generator, though, is generating kilowatts to megawatts of power. And it can't put that right into your house. It's got to be, that generator's who knows where from here. So it comes to a substation, and that's where the AC beauty really comes in. For transformers, where we transform one voltage level to another, for example, that generator may generate 20,000 volts. It's several hundred amperes. Some high voltage, high amperage stuff. But DC will not go through a transformer. So the AC will, because as AC goes around the coils inside the transformer, which is all a transformer is, it's coils of wire with an iron core. As the current goes back and forth, it generates a current on the output of it, and depending on how you do the windings, you can jack up the voltage, lower the current, you can jack up the current, lower the voltage, so that 20 or 30,000 volts coming in, go through a transformer, come out to be 117 when it gets down to us. It maybe the lines coming down by your house are still 10,000 volts. And you have that little transformer hanging on the pole, and it will convert it down to 120 or 220 if you have 220 service, which most of us do these days. And it will take care of that. But the reason we need AC is so that the transformer will work. Now, what about our radios? When I press the transmit key on my microphone, what am I doing? Why can't I just use pure DC for that? Anybody? We got to generate that wave. We have to have something that's going up and down in order to kick that wave out. The antenna in itself is somewhat like a transformer in that sense. Plus, inside the radio, DC is a solid line. How are we going to generate a 144 megahertz signal with DC? Can't do that. You've got to convert it with something else. So we use the DC to power an oscillator, which generates the frequency we're looking for, which is AC, and then it gets distributed through the radio and all the way out to the antenna. And the same thing coming back in. Signal comes in, the wave hits the antenna, creates a small current in that antenna, comes back in the radio, gets amplified, boosted up. It's an AC signal at that point. Then we can do some real tricks with that signal, mixing signals and all that, and get it down to something we can hear and extract the audio from it. And it's all done with AC. Without AC, we couldn't do that. We talk about our antennas being at resonance, which is a very important factor. When we're tuning an antenna, what we'd like to see at resonance is no resistance to capacitance, no resistance to inductance, just pure resistance by itself, and a low SWR. But we can fake it out, which is what most antenna tuners will actually do. They'll adjust those things so you get a good SWR, but they may not be a real good match. At resonance, we'll talk about that in a moment. Inductive reactance, inductive capacitance, which is the measure of resistance to AC in those components, will be zeroed out, basically. We'll talk more about that in a minute. But AC is extremely important for that reason. So back to the power line, generated by generator somewhere comes in. What about all those battery boxes we used at field day? We had radios that ran on AC. How did we get AC out of that battery box, which is a battery and DC? It had an inverter, which is really just an oscillator generating a 60 hertz frequency, running it through transformers and wave shaping as necessary. And it gives us 110 out to power whatever we're powering it with. So again, we're just converting the DC to AC, which is a great thing. Then, of course, there's the opposite we have to do on other occasions. We still need DC for a lot of different things in our radios, like the dial lights, for example, are important. They need DC. So we can go just the opposite. We can take the AC, run it through a process called rectification, and convert it very easily into DC. So we have good DC. So we can go either way. That's the good part about it all. We need DC. We need AC. They're both important. They both have their place. They behave differently, and we'll see that. Okay, alternating current starts at 0, rises above, falls below, and comes back up again. I'll show you a sine wave here in just a second. The frequency is how fast it goes up and down. Generators generate that. We measure it several different ways. We can measure it peak to peak, top to bottom. We can measure it just from 0 line to the top of one peak, or do root mean square or average, which are little mathematical sleight of hand tricks to make it easier to talk about. So that's the sine wave, basically. If you notice, it just goes up a certain distance, hits 0 again, goes down the same distance, comes back to 0. That would be one cycle, or in today's terminology, 1 hertz that it's gone through. So if it takes 1 second to go from here to there, that would be a 1 hertz signal. If this can go up and down like this between here and there 1,000,000 times in 1 second, then it would be a 1 megahertz signal. What we're looking at out of the wall is 60 hertz, so we're going to go up and down like this 60 times between here and there using that particular chart. Questions on that? We're good? Anytime, if you want to have a question, you want to make a comment, please just say so. Okay, a little more detail on all that good stuff. So looking at the amplitude of the signal, we measure the peak-to-peak value, which is talked about right there. We go from that peak to that peak, all the way up and down. What is the peak-to-peak value of that? We generally would measure that with an O-scope. The O-scope will let us see it. You can see it at the top, see it at the bottom, set your voltage scale, and you can actually measure it that way. So you can measure peak-to-peak. However, we can also just do peak, which goes from the center line up to the top, or vice versa, from the center line to the bottom, and measure just the peak. When we use our voltmeter, though, to measure that, what do we generally measure? Most voltmeters are going to measure RMS, or root mean square, this thing right here, which is the equivalent value if that were a DC signal heating an element. Now, why do we want to do that? Because on AC, we're peaking out here. Say if this is going into an electric heater, for example, we heat way up high, and then we go no heat at all. Then we heat again the other direction, and we come back to 0 again. and I hit the wrong button. And if it were DC, it would just run a straight line straight across and keep the element on all the time, wouldn't it? So when we average all of that out, if you please, and I have to watch using the term average because that's another measurement that we use. But when we average all of that out, then we get this thing called root mean square RMS amplitude, the equivalent to what would be done with if we were using DC. Because with that particular wave, sometimes we're going to have a real peak up here. We got some average in here, and we got some times when we don't have anything going. So we average all of that out, and we'll see the formulas for that here in just a second. The frequency then is the time for one cycle. I'll go from there to there. I usually like to go from the 0 line back to the 0 line instead of from the peaks. You can do it either way you want to. That's called the period, or the Greek letter tau, lowercase Greek letter tau. Looks like a T with kind of a bent top on it. Frequency of this thing is 1 divided by the time period for one cycle. And that will give you the actual frequency. So if we wanted to know the frequency in megahertz, 1 divided by 10 microseconds would give us a frequency. It's easy now when we play algebra with that and go back and forth. Okay, let's look at the next one. Same kind of thing, but a little bit more detail on it, showing the RMS value again. You do 0.707 times the peak value mathematically. Now, most of our multimeters do that automatically for us. You'll see a lot of multimeters advertised as true RMS reading. What does that mean? That just means they got a little bit better circuit in there to calculate what the real value of that AC signal really is. That's all. The average value, if you just average it out, it's about 63% of the total value. We don't generally use average that much. And again, we got the peak to peak, a single peak, and then the frequency that we're dealing with for one cycle across. Do you need to remember all these formulas and numbers? Probably not. Just nice information to know. All right. With that, let's do some of that stuff. And at this point, we're going to have to share a little bit, so kind of go around and do these things. There are 2 signal generators over there, and then 4 oscopes. Just hook up there. You can vary the signal generator, give you different frequencies if you want to. And then you have to sync the scope so it'll make sure the scope will see it and be stable for you. Most of the scopes are dual trace, meaning you got an A trace and a B trace. We're just going to use a single trace. So pardon? We're going to hook up an oscope to a signal generator over there. In Ron's case, he's got his right there. What do you mean? Of course you do. That's assuming it works, of course. I don't remember if I tested that thing before I came up here or not. I may not have. Okay, so that's one of the things really. The second thing we want to do is you have a little wall wart transformer. No, the little white transformer. This thing.
Oh, I don't.
That little guy. That's just a little rinky-dink transformer, 5 volts AC at 400 milliamps. The reason I have these or bought these particular things, number one, they were cheap, just to be real honest. I got a good deal on it. Way back when MCM Electronics was in business years ago, they had all this cheap stuff for sale. I got these something like 30 cents a piece or so. I don't know what it was. It wasn't much. But that's a secondary reason. The real reason is it's low voltage, low amperage. You're not going to get shocked off of that. You're not going to get hurt off. But anyway, coming out those two little wires, you should see pure 60 cycle AC or 60 hertz AC. So when you get where you can, I think there are enough outlets over there. Plug that little guy in, hook that up to the scope probes, and see if you can actually read the voltage that we have coming into the house. Through that, you should be able to see peak to peak, all that stuff. You should be able to measure it. Now, these scopes are not calibrated, so it won't be exactly, it may not even be real close to being accurate. But you get the idea of what we're seeing. And Ron and I will be around here for sure. We'll help you with the scope if you need help, and make it happen. Ready? Let's do it. Anybody? Oh, sorry, didn't mean to take that away. Okay, gang, what do we think? Do we need power for that? Are we? Okay, is there?
Do you happen to have a knife?
I do.
Bob definitely has the tools.
You could just cut it.
Yeah.
Or we could probably cheat.
So we'll first, like, I want to see how you actually use it.
There we go.
Thank you.
And we can reuse it. Okay, gang, what do we think? Okay, let's disconnect all this stuff. And just kind of let them hang wherever they will. Yeah, right. I clipped them all together. I'm doing really good, aren't I? So if I'm going to take this little guy and say I'm going to hook him up to this one, I have to pull that off. Okay, right now he says he is on sine wave.
This is the frequency generator?
It's a frequency generator. I'm running in generator mode. This is also a counter, but right now we're using it as a generator.
I mean, it's not connected to anything other than just.
It's just plugged into AC, that's all. Correct. Okay, so we're on the 2 megahertz scale. So we should be generating a 2058 signal. We can change it a little bit by there. Let's take it down to 200K. Let's see if we can generate about 200 hertz. That's close. Okay, and we hook this little guy into here. That's the input, sorry. And into the output right there. And we should get something. Amplitude. Okay, we are not triggered, are we? Sometimes they want to be contrary. And then you can always, if you run into trouble getting the thing to sync up like it's supposed to, you can always cheat with a scope like this one. And go auto. And turn that off, run. And it is not doing much, is it? Wow. Well, that guy's just not cooperating at all. He hasn't been used in a long time, so that may be part of his problem. Come on. Trying to get this guy to give me a frequency out. He is just not cooperating. Let's see if the 50 hertz works. Things don't always work like you wish they would. And that doesn't control that anymore. Don't need a DC offset, don't need symmetry, TTL out. I'm in the wrong thing, no wonder. Let's try that one. There we go. All right, I'll get rid of the menu. Okay, it helps if I go to the right output. My mistake. Okay, so what we've got going there then is, this tells us that we're running 5 volts per 5 volts per block. So I've got about 2.5 there, and 5, 10, and 2.5, 2.5. So that's about 15 volts there. I can change that from here if I wanted to. Take it down to that's about 10 volts. And we're on 2 microseconds per division here. This is where I can move it back and forth. So if I go right about there, and I measure from here to there, so at 1, 2, 2.5 times 2 microseconds. 2.5 times 2 is 5, so 5 microseconds. So what's the frequency, somebody? 1 divided by 0.00025. This scope cheats. It's actually 199.954 kilohertz. This actually measures it for you. Obviously, this is a much newer instrument than these old guys over here. But that's kind of the idea behind that. And again, actually, we can tweak it and see where it goes. And then we want to go up, back up to that one. Boom, we're way up there. Now let's go auto again. Auto basically just adjusts the trigger levels and all that stuff to give you a good display, so you don't have to mess with it. So there we go. And now we're running at 2.18 megahertz. We're supposed to be able to go to 2 megahertz, so we're pretty much maxed out right there. And the two are pretty close. Considering neither one of them's calibrated, that's not bad.
And why would we want to do this?
This is just to demonstrate looking at the waveforms. And if you're troubleshooting, oftentimes that will come in handy. You're troubleshooting, and you're say troubleshooting a receiver and has no audio coming out the speakers. So you take a signal generator, put a signal in on the input of the antenna, and where the output's supposed to come out as audio, you put the scope on it and see if you have a signal there. Well, I got a signal. Okay, so that's it. I've got audio, but it's not getting to the speaker. Then I go to the next amplifier stage. Do I have audio here? Do I have it here? Do I have it here? Oh, this stage is out. So I know this transistor or whatever in that circuit is where the breakdown is. It's used for tracing.
So the signal generator is just generating the signal on a certain freak, and then
Exactly. Yeah, exactly.
If that's everything the receiver's working
Exactly. That's one of the easy illustrations. Yes. You can also use a scope to see the output of your transmitter to see how pure your waveform is coming out of your transmitter. It takes another little piece of equipment to do that, to basically downshift it where the scope can see it. The scopes can't see anything that fast, but a downshift where you can actually see it, you can actually see what your voice looks like in waveforms as it comes out. So if you're doing a whistle and it's whistling into your microphone, and you got that, oh, that's perfect. But if this thing is clipped at the top or it's really distorted, then we got a lot of distortion in our audio. Bad microphone, gain is not set right, or there's something in the audio amplifier for our speech is not right. So there's all kinds of different ways for using that sort of stuff. This is just demonstrating it, as I said. Now, if we go back to here, this is just plain old AC at this point coming out here.
Every good scope, if you don't have a calibrator, don't buy it. That's a good way of evaluating.
So we'll just do this. I love this little guy. The auto is so much faster than having to sync it up. Okay, and that's our output from our little cheapy block over there. You notice it's not a real good sine wave. It's not bad, but it's not great. So, okay, and it says it is 60.00457. Well, that's varying a little bit. So pretty stable. 0.0001.999. So the frequency is fluctuating ever so slightly, which is normal. It's hard to keep everything exact, but you get the idea behind it. And then the value of it, again, 5 volts per. So let's see, is that right? And I'm probably on times 10. By the way, one of the other little gotchas you have to watch out for on the probe. There's a setting times 1 or times 10. So if it's on times 1, 1 volt in gives 1 volt out. Times 10, 1 volt in gives 1/10 of a volt out. So you can use it like an attenuator. Okay, so let's see if I'm anywhere near right on that one. Okay, of course, this transformer is running open circuit. It doesn't have any kind of load on it to pull the voltage down. So it's going to be a little higher than what it's rated at. It's supposed to be a 5 volt one, but it's going to be more than that. So again, we're looking at 5 volts per division. And let me put that right on the line there. So that's 5, 10, 15. It's actually about 20 volts coming out of that guy because it has no load on it. Now, if I put a resistor across these two leads, that should drop back down to about 5 volts, and it just cover up, from here to there, one scale. Or the scope would downshift to a different voltage reading to give you a bigger picture. And you can, of course, I'm doing it automatically, but you can control this value with these knobs here. I can change the voltage values, as you can see. Go to 2 volts per division, 5 volts, 10 volts per division. And you go, and it'll go all way down to microvolts, 20 microvolts. Back to there. So you can play around with those things. And likewise, you can do the same thing with the scale. You can change the time base to spread it out or shrink it down to make it easy to read. If it's like that, that's kind of hard to read that. We'll pull it up there a little bit more like that. Then I can say go from there to there, and I can measure that much easier. Of course, on this scope, it's telling you what it is on the frequency, so that's kind of nice. These guys, these are antiques. Literally, they're antiques. These scopes are probably 40 years old. That one over there was one I bought myself when I was still in the service prior to '85. I'm guessing I bought that about 1980. And it's still working, which is the amazing part about the thing. And of course, what you're seeing on it is it's internal. It has an internal generator. Most scopes have an internal generator. Give you usually a 1 kilohertz signal at about 1 volt or so, and that's basically used for 2 things: one, to see if it's working, and the second thing, if you notice on these probes, let me just take this one off of here. Notice there's a little screwdriver opening inside there. Okay, if this probe is not compensated correctly, not set correctly, then you get this rounding that you see right there. So I can turn that little screw and make it a nice, solid, square wave. I can compensate for that to make it nice and square. So that one has not been, obviously has not been compensated, so. But that's kind of the idea behind it. But we should be able to do the same thing on this guy. And I'm just going to have to hold that guy since I don't have a little clip that goes with it. Okay, so we're way off all the way around here. So. And then we got to adjust our voltage for division. Okay, there we go. Let's see, that's up and down. Where's my left, right? There we go. So I can start there. 1, 2, 3, and a tad over 3 divisions, and I'm running. Then in this case, I have to read it though. I'm doing 5 milliseconds per division, so I got 25 milliseconds. We calculate that out. It should come out right at 60 hertz. And then voltage-wise, we got to do this manually. Check the probe I'm on ×1, so it's not attenuating. We're actually doing 2 volts per division, so we got 2, 4, 6, 8, 9, about 9 volts coming out of that with no load on it. So that's kind of the idea behind it. And that's it. Thoughts or questions on that? If you want to try it, go ahead. And let's see, while we're doing that, get this guy fired up. See if we can overload the building. Let's see, I need to go get some leads. Actually, I'll cheat. I'll just use this lead.
Thank you.
10 hertz done. There we go. Can you get him to go?
Assuming it's this one.
Okay, first thing you want to do is just, we got a trace on. Probably need to go with this guy's. And then we have to move it left and right.
Which
One is this one. Kind of get it about where you kind of in the middle, and then use that one, move it up and down, kind of get it centered up there. Now then we can turn that one to try to get an actual waveform on the screen. Keep going. Oh, the other way. Okay, then let's move him back over again. Okay, and where are we at? And of course, that's 60 hertz, so that's why you got the flicker. And of course, you can move it back and forth, up and down, however you need to move it to get it where you want it.
I'm watching.
Even though, I mean, it's really slow.
Somebody just gave me one of these, and I haven't even cleaned it off yet to play with it.
Oops, I'm doing the right thing at the wrong time. Come on, Bob, give it a program.
We're going to be using these over there anymore? Just leave this here as soon as
You can just leave it there if you want to.
Yeah, I'm gonna try it. I've only powered it on and never knew how to use it.
Okay, trying to get this guy to come in there. Oh, wait there. He is not going to do it. We'll get that one later. We'll worry about frequency counters later. Anyhow, that's kind of what it's all about, just for fun.
I think this is it. the waves over my head.
It's like drinking from a fire hose. It kind of is, yeah. It's kind of like drinking from a fire hose.
But it's, I mean, but it's, if you're having issues in your shack or whatever, then, this is what you can use to make sure everything's working the way it's
And
supposed to
if you
work.
like to tinker or experiment, then that's when it comes in handy. A little later at the end of the class, we're going to put a little oscillator module on our breadboard and generate a signal and look at it. And it'll be a square wave. And then we're going to put a filter on it and convert it to a sine wave. So you bring it back over here, hook it up, and you'll actually get to see that happen. Kind of give it somewhat more of a practical application. Okay. How we doing, guys? You guys get it to play?
We're gonna find out. I don't know what I'm doing.
Okay.
See if the magic smoke comes out. Is that plugged in? Maybe it's backwards.
Okay. Do you have an auto button? You do.
Oh, it's not in the right. Oh, this is not in the right spot. Hopefully I didn't burn that.
Okay. I would recommend you put it on channel 1, which is this one.
Oh, so it's not negative or positive.
Not for this. No. Just use channel 1. There we go.
And I plug it into
Okay, we're on channel 1. Now, it doesn't matter. Since it's AC and it's alternating up and down, it doesn't matter. Okay, and then hook your ground onto the other one. There we go. Okay. Sometimes you got to do the auto, and then run. Oh well, let's go to channel 1. Oh, those don't stay in, do they? Oh, there's our trace. And just drop it all the way to the bottom. Okay, what's our coupling? That's a marker. Well, I'm not sure. Let's see. We're on channel 1 auto. Okay, that should work. 5 ohms per division.
Could be the switches here.
Well, it could be, but it's not likely to be. Run, okay. Stop. Run. Auto. Wow, I don't know why that's not showing us something there. Let's see, that's left, right. That's just a marker. Well, I need to read the book on that guy and see what he needs to do. That's terrible, but I don't know what else to tell you. We'd have to. I think you and I need to get together one evening or something and play with that guy. It's a nice little scope. It's 100 megahertz scope, which is a real good bandwidth. It's a nice little scope. Just unfortunately, we're going to have to spend some time with RTFM. Read the fine man.
And you put you solder a little wire, a couple of turns to it, and you hoist that up onto your antenna. You put it up there. When you key up the bulb light. Because the light bulb doesn't care. Yeah, the light bulb doesn't care. AC, DC, RF, power, it's just power, right? So it just lights up. It's just like
Yes.
No question. Good job.
Oh, thank you.
So that was a great.
Okay, gang, how we doing? Don't forget the donuts in the back, and there's water in the cooler if you need either of those. And restrooms are somewhere out down the hall. Everybody okay? Okay. Okay, a couple of you asked a question, and it's a very legitimate question. Why are we doing this? What's the point behind it? I understand that. This is demo. Really, that's all this is. We're just demoing kind of what does some of this stuff look like that's out there? What do some of the tools look like? Would you use this every day? Not unless you're a technician doing repair work or something like that, or design work or something. Or what I really hope you'll do is you'll buy your own breadboard, buy you a selection of components, and go play with this stuff. See how it works. Make it happen, and check. Buy you a little cheapy scope, and go play with this stuff. I mean, you don't have to spend tons and tons of money for this stuff. Of course you can. That's not a problem if you want to. For example. Those two little guys are made by Velleman Instruments. They're about $50 to $75 a piece. One is actually an O-scope and the other is a signal generator. Built-in rechargeable batteries, and they work like a champ. I mean, it's a tiny little scope, but it works, and it's got an auto on it, which is really nice. So those work really good, and that's just another thing you can do if you want to do, if you want to have something to play with. But I mean, you don't have to go out and spend $2,000 for a fancy O-scope. You can, if you got lots of bucks and want to do that, sure. But most of us don't, and we don't have a reason for that. But you can get something like that. Those work really, really well. And then if you want something a little more portable. This particular one is no longer made, but its successor is available. This is a multi-purpose, do everything. I believe it was right at $100 when I bought it. It wasn't terribly expensive, but it does everything. It's a voltmeter, an O-scope, signal generator, all built into one instrument, and has rechargeable batteries in it, so you don't have to have it plugged in to make it work. And it just works like a champ. It comes up, looks like a computer. Says who we are, we're coming up, and then comes up and gives you a trace. It's a Hantek, H-A-N-T-E-K. But no, they're new. These, of course, they're all made in China, as you well know. And now, when the tariffs come in, that may change. None of us really knows what that's going to mean. But when I bought this, obviously tariffs were not part of the discussion. Yeah, some of the stuff I know has already gone up. Some of it they've jacked up the prices in anticipation of the fact that the prices will go up. But this little guy's pretty handy. It's pretty reliable. It's pretty accurate. It's not bad. Just to see what a waveform looks like. As I said, you can measure voltage and current, a few things, resistance, and it's got a full-blown digital multimeter built into it. So it's not bad. And then when you shut it down, it says in and goes processor control, obviously. So there's some options out there. One of my, I have no idea where I set that thing down now. One of my little pride and joy things, and I can't find it now, is this old O-scope that I pulled out of mothballs.
Is it setting up over there? On the other table?
I took it out and did something with it, but I have no clue what. It's a little black box about this big, about that long.
Is that not it back there on top of the?
Did I leave it? I thought I had it in my hand when I came back here, and I don't know if I set it down here someplace or not. Golly. Nope, that's not it. That's a frequency counter. There it is right there. I got that far and was talking to somebody else and forgot where I was. Let me come back around to the front again. This guy is literally older than the hills, but it's a great little scope. It's not, you can't even buy one. They don't make these anymore. This thing's about 45 years old right now, I guess. Fortunately, I had it in a plastic box so it was protected, and it uses 3 lead acid sealed batteries in the thing, which costs now $16 a piece. I just put new batteries in it, but it works. You just flip the switch on, and boom, it comes up with a trace, and you're good to go. And it works like a champ after all that time. I did go in and clean all the switches and contacts and all that, but you can find some of these kind of things like on eBay or used market and get a good deal on something like that, even if you wanted to do it. So just FYI. Okay. Yes.
How risky is it to buy something
How risky is it to buy something like that at a ham fest? It can be very risky depending. If you're at a ham fest where they have power and you can power it on and see it work, then you're pretty likely to be okay. If it's where there's no power and the guy just says, well, I checked it and it worked 5 years ago, then lower the price. You know? Yes.
And you can test the radio, you can test it at all the frequencies, the power, you can test power supply, you can test equipment, you can test passes, anything you want to test it. They bring in their whole shop, it's a lot of fun.
Yeah, there are a couple of hams in this area that are well equipped. And they bring all that stuff in, set up a table in a ham fest, they'll test anything that you want to buy. That way it eliminates most of the risk, at least. Of course, you know, you buy a radio that's 20 years old and is working fine today, tomorrow it may not. You know, that's just a gamble you take, obviously. But most of this stuff is pretty solid. This old multimeter, so it's about the same age as most of this other stuff. It's probably 40 years old, made by Syncor. Syncor's still in business, but they don't make this kind of equipment anymore. What was really weird, it had an on-off switch in the probe, so you didn't have to physically turn it on. You could just push the button. The display comes on, you can measure whatever. So anyway, they used to tout this thing as being the rugged meter. And the way they proved that was they'd take it from this angle and throw it across the room on the floor. Literally. Pick it up and it work. Yeah, like a Timex watch basically, and of course it'd still be working. I've seen the guy also take this thing and hold it by the test leads and swing it like this as hard as he could, and it'd still work, you know. And the test leads didn't pull loose. So they were well made. Anyway, okay, getting sidetracked with that. So we played with the scopes just a little bit, looking at some of the AC waveforms. You see what's going on. If it were DC, it would just be a straight line. With AC, you see some sort of wave shape. Did you notice that the AC coming out of those little transformers was not real clean, not clean AC? Probably because of the internal workings, not that good at transformers would be my guess. Plus the voltages are high because there's no load on it. If you put a load across it, it would lower the voltage back down where it should be. Now, if you come back for the solid state class, we'll take those same little transformers and we'll plug them into a breadboard, put a rectifier on it, a capacitor on it, and build a power supply. And you get to see us convert the AC back to DC again. So you get to do that again when we do that. Okay, let's talk about components a little bit. Capacitors. What does the name imply? Or does it? Capacity? Okay, that's the idea behind it. Really, a capacitor, in a crazy sense, is just a small, very very short life battery. You take a capacitor, you charge it up with something or another, and it holds the charge. It may hold it for a little while. It may discharge it very quickly. It just all depends on how it's hooked up and what you're doing with it. One of the old things that used to be so much fun was to take a capacitor. This is only 35 volts, so it's not a good one. But you get one of those that's a 250 volt capacitor, put it across a big power supply, charge it up to 250 volts, and toss it to somebody. And of course, they grab it, and of course, it's a short discharge, you know, but it would get your attention. It would light your running lights, let's say. But anyway, that particular capacitor is a filter capacitor. It's a big honker, a big handful thing. Then they all go all the way down to little bitty tiny things. Though you can't really see it from back there. Those capacitors are little tiny things in there, smaller than a dime. And value-wise, they go all over the place. But anyway, what do they do? They store a charge. That's their whole point in life. Why would we want to do that? Because when we pair a capacitor with a resistor, we can calculate a time constant. We're starting working toward building an oscillator. We can calculate how quickly that capacitor will charge and discharge. We can adjust that with the values of the capacitor and the resistor. We can create an oscillator of a particular value quite easily by knowing that. So that's where we're going with that. What is a capacitor? Basically, it's two pieces of some kind of conductive material with an insulator in between. It can be mica as an insulator. It can be paper as an insulator. It can be mylar as an insulator. It can be any number of things. And when you need to get a whole lot more capacitance, that hold a lot more, like this guy, then you roll the thing up. You take 2 sheets of aluminum foil, long thin sheets of aluminum foil, put the paper between, and you roll it up. And that it gives it additional capacity to hold the charge that it has. So we play with the plates and the material and the insulator in between to adjust the values of the capacitor. It's measured in farads, comes from Michael Faraday's name. A farad is a humongous amount of capacitance. It's not something any of us will see really probably in our lifetime. Now, there's ways to cheat. You can use a transistorized circuit hooked to a capacitor and make it look like it's a farad capacitor. And a lot of the high-powered stereos in cars, the ones that blow the windshields out when they get so loud, those take so much current from the car battery that the battery can't supply enough current to keep that thing going. And they'll actually use these amplified capacitors to hold that charge for those basic bass boost or bass burst of the speakers, so that it won't take the battery down completely, and the sound will still be pure. But there are ways to get around. We don't generally see that. That's kind of a far out application, but it can happen. So instead of measuring farads, what do we measure in? Usually microfarads, millionths of a farad. And then we go on down from there to, in the old days we called it microfarads. Nowadays it's called picofarads. So micro means 1/1,000,000th of a farad. So what is a micro or a picofarad? 1 to the, or 10 to the minus 12, 6, 12, minus 12, right? So that's where all that metric stuff comes into play there when you shuffle back and forth between these things. Generally speaking, microfarads and picofarads are what we'll see most of today. If you get picked up a schematic for a radio and you're looking through there, most of those things would be labeled. They would be labeled and would be listed as picofarads or microfarads. Now, with a capacitor, the resistance to AC on a capacitor will change based on the value of the capacitor, which is a great thing, because we're charging and discharging. So we put AC across it, we're going to charge it and discharge it again, back and forth. So capacitors found a great application, as I've said, in oscillators, because we can measure that charge and discharge time. Generally, what we like to say with capacitors, that they will block DC but pass AC. Because if you put DC on a capacitor, it will simply charge it up and then just sit there. There's no way to discharge it. But when we put AC across it, AC will come in, charge it, come back the other way and discharge it, charge it, discharge it, back and forth. Now, some capacitors are made for DC, like this big guy I was showing you here just a second ago. This is a 10,000 microfarad at 35 volts DC capacitor. It's a filter capacitor. It's made to be attached to something in DC. The idea being you have the output of a power supply, comes through this guy, this stabilizes the output so it remains nice and smooth. If this were not there, the DC coming out of that power supply, if you looked at it on the oscilloscope, may do a little bit of this. You put this on there, it filters it or smooths it so that it fills in the gaps and takes care of making the current coming out of a supply nice and smooth. But how do we rate the things? Well, we already talked about the measurement. They're measured in farads, and then they're rated by voltage, the amount of voltage that they can handle. Anybody know on antennas what kind of voltages you can experience at the middle and the ends of an antenna? Totally not. They tell you not to touch it. There's a reason for that. There's a reason for that. Weird things happen between the radio down the coax and into the antenna. Even though that radio is running on only 12 volts, the RF coming out the ends or the middle of the antenna, depending on where you tap it, can be several thousand volts. It really can. I mean, it's like a transformer action. It really gets up there. That's why you get an RF burn from it. So we rate capacitors the same way, basically, by the voltage that they can handle. You'll see if you're doing an antenna matching network, oftentimes there'll be a capacitor specified that you need a 20 or 21 picofarad capacitor at 5,000 volts. 5,000 volts? Why? Because that crazy antenna might generate, 1,000, 1,500, 2,000 volts. So you need that voltage rating for that. Then on the other hand, your little transistor radio, all it needs is a 10-volt rating. It's no big deal. It's not doing anything that's exotic. So we see those two things that happen. Now then, let me just take one.
Is it gonna shock me? Is this?
It's not going. None of them are charged. No, none of them are charged. Yeah, I wouldn't do anything bad to you. That's for sure. Not like that. Okay, where are they? Well, I can find everything but the right thing. Somewhere here, I thought I had a bunch of small value capacitors. I thought I had something had a bunch of these little guys like this in it.
Is it these?
That's looking right at them. Looking right at them. Okay, those are largely filter capacitors that you're looking at. I'm going to pass these around. Take one of these or one or two of these. We're going to look at values here in just a moment. You're going to see how interesting it is to look at values for capacitors. It can be a real challenge to see it mildly. I can get the staple out of here.
Here, I'll have this out.
You get that staple out of there. You're going to pass around another bag of capacitors with some smaller values. Just take pick two or three out of this bag and hang on to them. And then we're going to talk. Yeah. Now, you know why I was wrestling with it. Hello? Uh-oh, I lost it, Lance. There we go. We're having a hard time getting this thing open. Here you go.
I think we got it.
Got it? Cut it out if you have to. Here, let me just catch it like this. There we go. Okay, sorry about it. Couldn't get the bag open. That was a good staple. Just take two or three of these things. You have a handout that talks about capacitor values and how to read those things. And the thing you're going to find out from that is that they don't all cooperate. Some of these things just don't work quite like we wish they would. Okay. While we're getting that done, I think I've got enough of these. We put one of these at each row, so we're going to have to kind of pass it up and down the row a little bit.
You got a magnifying glass?
Okay, the question was just asked, do I have a magnifying glass? The answer is yes.
You can use your phone.
And there's a reason for that. You'll notice some of those numbers are really tiny unless you have really good eyesight. It's pretty hard to read those things. So I keep a magnifying glass handy. Or if you have the one on your phone, of course, that's good too. Yeah. Okay, let me get this one on the back row. Okay. Okay, those RCL meters that I just passed out, which unfortunately we got one to a row, so you have to play with it and pass it down. But depending on the meter, you hook up the capacitor to the two leads, and then either turn it on. Some you have to select the value, guess at the value what it's going to be, and tune it in. Others will be a little more automatic than that. So you kind of got to play with it and figure out what the meter wants. It should give you a crude guesstimate of the capacitance of any of those capacitors that you have as samples. That's the whole point behind it. Do you have capacitance on your meter?
Probably not.
No, you don't have.
Got inductance and
Sir?
Inductance and, but there should be,
Yeah, just use the leads there.
there should be.
And then you got to
okay.
set it for capacitance or inductance.
capacitor that you want. This is by Sprague. So this is a high quality brand. And here you can see this is negative because it's connected to the cam. Positive is insulated. Copies the battery construction. They didn't invent anything new. They just went with the flow. It's also an 85 degrees C. And look what it's reading.
90.
Okay.
Okay, and then he said for, where.
Right.
So
You get it to work.
if I've got a 10,000 peak That's 10,000 picofarads?
Micro. The
Micro.
little U thing means micro.
Okay. So
Oh, by the way, excuse me, by the way, on those big capacitors, you notice where they've got a minus marked on one side? Those are polarity conscious. So when you hook those to the meter, make sure you hook the black lead to the minus to get a good reading. Okay, now back to
Okay, so
the
how do I know which side of the meter to use?
Okay.
and So I don't.
So these are, we're using the LC capacitance and the inductance here. Okay, and then we're gonna hook these two leads to here. Black will go to the minus side.
No, it's the minus. Where does it say that?
That little stripe down the side.
The stripe
That's supposed to be a minus.
is the minus. So this is minus? This is minus? And then how do I know where to set the?
Okay, I'll show you. Go ahead and hook him up. We'll play with it just a little. Okay, now we're measuring capacitance. So it's right now, it's over here on L, if we want to go to C. I'm looking upside, here we go. So we started 200, 10,000, we'll start there.
That's 1,000
So you
micro.
start at the highest and then
Start
you
and
go
work
down so
backwards.
that you don't.
And work
Yeah,
backwards.
yeah, right.
We're at 1,000 here. This is 10,000 microfarads.
Okay, which means it's not going to give you a good reading. It's not going to read right. See, as you
mean
can see,
because
it's
it can't
bouncing
go up
off.
that high?
It exceeds the capacity of the meter itself.
So do we just need to do a smaller one? Is
So,
that
yeah,
the
so you're
problem?
going to, now, the truth of the matter is, this may have deteriorated, so it may not have,
It may not have 1,000.
it may not have what it's supposed to have, exactly. So let's try another one now.
Let's try this.
That one's, what is that one?
Now this, I can't tell.
That's
'cause
100
it's minus and
microfarads.
minus.
No, let's say, this is the minus, this is the plus. Wait a minute, no, I said it wrong. It's pointing to the minus. The arrow points, this is the minus.
Okay.
And that's a 450 volt one. If we had a way, if we had a way that we could charge it up, we could charge it up and toss it to somebody.
I bet we got enough.
And that's
to figure
100
that out.
microfarads.
So it's
Okay.
reading
It's reading
125.
125, which is not unusual.
For it
So
to
we
be a
could
little
probably
high.
come down to the next scale. There we go, 117. That's not bad. That's pretty close. Capacitors will vary very widely.
Can I hurt a meter by having it set on the wrong?
No, it won't hurt. It won't hurt. It just won't read right. Yeah, it won't hurt anything.
So you start here, obviously, so you don't blow
And,
up.
and go down until you find the one that matches.
So try one of these little guys.
Okay, now, we can go for a little.
So we gotta look at the things to figure out.
If you can look at that, if you can, some of them are just marked, and some of them are not marked very well at all. Some have colors, some don't.
That's 100 volts. Could that be? No. 100 V.
And some of them can be a little hard to see. I'd say just hook it up and see where it goes. Now, these guys are not, they're not polarity conscious, they don't care.
Just, and what, how do you decide if it's polarity conscious, just the size of it?
If it has the minus marked on one side,
Okay, if it doesn't have a minus, then
it's not marked, no, you don't have to worry about it.
Okay, and so where would we start on this?
That's a good place. It's gonna be a small value, so it's not gonna be much. Okay, so we're barely reading, because we go down one more. 0.02 microfarads, keep going down. 0.1 microfarad, go to nanofarads. Now, I think we get a better reading as we keep going down.
10.9, so now we're,
It's 10.9 nanofarads, and you probably can go down one step still further. 11.01 nanofarads. Now, 2 nanofarads is going to be over range, so it won't go.
But I can't hurt it by
It won't hurt it to do it. No, it just won't give you. It just gives you a bogus reading.
okay, so you know, that's kind of good, you know, you're between
So
those.
it's 11 nanofarads,
So I
which is
have
10 to the
a-
minus 9.
I have a fluke meter that's pretty good. It should be able to do this, right?
May or may not.
Okay.
A lot of the meters now do have a capacitance scale on them, but most of the older ones do not. Okay? You can help the other guys down there when you get to it. What do you think, guys?
I have no idea what I'm doing.
Well, good, I'm glad. You're right at home. You hadn't got the meter yet, though, that's the problem. We'll get the meter passed down to you here in just a second. When you get through with the meter, be sure to pass it down to the next person down, since we don't have enough to go all the way around. Making headway?
I don't know.
That's a good answer.
This is mine, because it's on capacitance, but I don't know if it actually measures one of these things.
Capacitance, okay. Nanofarads.
This does. And then, how do you
Okay,
tell
now watch out for this. Sometimes, no, on this one doesn't matter. Okay, sometimes you have separate jacks here for capacitance, but that one doesn't have. Let's go to something a little smaller and see what we get there. And that one's got a minus on it, so we'll keep the minus and plus separate. 0.03. Oh, come on now. 185 microfarads. See the little micro right there? Well, yours is auto range. I'm having a hard time holding it steady. 185 microfarads, and it's printed 180. That's pretty close. Pretty close.
Okay.
Capacitors are very, very, very wide. When you get these guys, they'll be a lot smaller values. Let me go ahead and take your meter here down here and pass it on down. Okay, they use. Here you go. Here you go. Try that one. Okay, basically. Okay, those are not polarity sensitive, so just clip him on. Okay, now we're already on, and we're on 200 microfarads. Let's take it down some. Okay, starting to get a reading now. How far down can we go? Okay, it's over 200 picofarad. So it looks like it's 0.743 nanofarads, which would be.
That's cool.
0.743, so about 700, right up to 750 picofarads.
Wow. That's cool.
And that's the idea behind it. Now these guys, this is where you got the minus marking.
Yeah.
So this is the minus. You can also tell because the positive, like the batteries, this comes out of an insulated side and that's hooked to the back.
Oh, really?
So we can just hook him up like so. Okay, now he's way down, so we're going to take him way on up here. What's it supposed to be, by the way?
30,000.
Oh, we're still on. Okay, now we're getting
988.
okay 989 for 1,000. So that's pretty close. In most cases they're read a little over, but sometimes they read under. It just kind of depends. That's the idea behind it.
I never noticed that about capacitors about that.
Okay, you guys. Rob, you giving them the lesson there. All right, good deal. Okay, he's got that meter. Have you guys had a chance to work with the meter yet? Here, use my little good one.
It's trying to blow this thing up.
That one's good. The only thing you have to watch with this one is be sure on these guys that are polarized. The negative, it's like a battery. You see it has a metal end in it. The other end will have an insulated end for the positive. Make sure the black hooks to the negative.
The black hooks to the negative, so the black is
And the red to positive.
correct, right?
No.
No?
Otherwise, no, that's positive. That's looking at your battery. Okay, there you go. Okay, and then you just tap the on button. And it says, okay, basically it's doing a self-calibration during that time. And then it'll come back and it'll say, this is, just like that. I love that little meter. I mean, it is so precise.
Are these polarized?
Yes. Yes. See, you got the minus on the side. Anytime you see the little minus stripe down the side, means it's polarized. And the little arrow will point toward the,
Is that what this is?
Uh-huh.
Is minus?
Uh-huh.
Okay. See, I don't know how to read this stuff. Interesting.
okay? You don't have to do anything, just hook up the next one and hit the on button again, and it'll restart the test. It'll hold this display for, I don't know what, 15, 20 seconds or something, and then it'll blank itself and start over. Okay, you just tap the on button again. $30 microfarad. What's it supposed to be?
It says 33.
Okay, pretty close.
Interesting. Okay.
Pretty close.
Could you use this to build like an inductance coil?
Sure.
I've got a meter. It's a blue
Absolutely.
one. I can't remember the name of it now.
Yeah.
But when I was playing with the inductance coils for.
You could sure, yeah, absolutely. This does resistance, capacitors, and inductors, and it's very, it'll read down, into the microhenries, 1 or 2 microhenries very easily. And likewise, resistors, it'll measure, if you have a real high tolerance resistors, it'll measure those things down and give you a really good read. Those work, and they just work. These other meters, you got to set the range and mess with them and all that. This, you just push the button. So I use that one all the time. I love that one. It just works. And you can do the same thing with the little ones.
Now, these are also polarized or no?
No, those are not polarized. If you don't have a stripe down the side, they're not polarized. See, like this one is polarized. It's got a stripe.
So this one is polarized.
These little guys, you want to be sure when you measure those that you don't hold the leads because your body capacitance. Now on these, it's not going to matter, but on these little guys, it will matter.
You start staking exactly who was.
440. This one's. Yeah, well, I can't even tell. It's cut off.
That's the temperature. It must be on the other side, I hope.
Take this off. Interesting.
Oh, here we go. It's supposed to be a 470, kind of ran off the edge. It's 470. So 440, that's close enough for these guys. Like I said, the tolerances on these things are way wide. They're usually like plus or minus 25%. Then when you get to the picofarad one, though, then you can start getting into some real close tolerances if you want to do that. 3.18 nanofarad.
Now this has 0.004.
0.004 microfarads, which is 3.18 nanofarad. Yep.
That's neat.
Okay. What do we think, gang? Everybody get a chance to play a little bit? Okay. And you'll probably notice if you try to read those numbers on those things, it can be a little bit crazy, to say the least. Okay, gang, everybody have a chance to play at least a little bit, kind of get the idea. Okay, let's keep it moving, because our time's getting away from us, so we're going to have to keep moving. Okay, let's add some more fuel to the proverbial flame here. Time constants. This is where we're talking about we can calculate the charge and discharge time for a capacitor, which becomes very important when we're doing oscillators and things like that. We need to know that. The lowercase Greek letter tau, which kind of looks like a T with a little squiggly in the top part of the T. The capacitor will charge up according to its value. The greater the value, the longer it will take for it to charge. I guess that makes sense, doesn't it? Likewise, the greater the value, the longer it will take for it to discharge, to lose its voltage. Now, we add a resistor in there to the circuit, and then between the resistor and the capacitor, we can actually calculate what that time is. Now, the crazy thing in the calculating time constants, though, we don't take the charge level up to 100%. Charge level is, the capacitor is considered charged if the charge level is 63% of the applied voltage. So if we're applying 10 volts and it charges up to 6.3 volts, it will be considered charged. Likewise, when we discharge it, we don't have to take it all the way down to 0. And there's some reasons for that. If you looked at it on an O-scope where you can see the charge curve, that last little bit of charge between 63 and 100, the charge will go kind of linear, and then all of a sudden it'll taper, and it'll take forever to reach that last little bit. Coming down is the same way. It'll come down rapidly down to 36 or so percent, and then it will very slowly discharge past that. So that's why we use those two numbers. Time constant is equal to resistance times capacitance measured in farads. So we have a 100 k ohm resistor and a 1 microfarad capacitor. We multiply those two together, and you got the time it takes for it to go through a charge cycle, charge-discharge cycle. So here's what we're looking at. In this particular example anyway, we've got a 100,000 ohm resistor in there. We got a capacitor of 100 microfarads. To make it simple, we use the 10-volt battery. Makes it easy, right? And we put a voltmeter across the capacitor. Switch is open. We read basically nothing unless there was some residual charge there, which is not likely. So we're reading nothing. And then we close the switch. How long is it going to take for this voltmeter to read 6.3 volts, which would be considered charge for a capacitor? What was the formula again? R times C. Somebody got with a calculator, multiply 100,000 times 0.0001. What do we get for a frequency? $100,000 times 0.0001 gives us 100 K, 100 kilohertz, or 100,000 hertz, or 100 kilohertz. Okay, so we've just generated, essentially we've had the basic makings for a 100 kilohertz oscillator there. All we need is some way to make it charge and discharge, which is a whole other discussion. But that's the idea behind it. Now, can we actually see this happen? Yes, we actually can, so let's do that. You have the breadboard. You should have a 9-volt battery and a 9-volt battery clamp to go on it. We're going to use 9 volts instead of 10. I don't have anything that does 10 volts. Okay. And then you're going to need to find yourself a capacitor of some value, at least 100 microfarads or greater. So you're going to need a fairly large capacity capacitor. You may have to dig through the bag to find one of those. And then you're going to need a fairly high value resistor, which I just happen to have a bag of here somewhere. Where is that 100 bag of resistors I got there? What? Does the voltage matter? Yes. The capacitor will be rated at so many volts. Anything we have here will be rated under the 9 volts we're using. But if we were in a real circuit where we might have 50 or 75 volts, we'd have to be really aware of that. Yes, we really would. Yeah. Now, if you, the electrolytics, remember they got the little stripe on them with the minus? So be sure to observe the minus and the plus on the capacitors. Make sure the minus of the capacitor goes to the minus of the battery. No, that's not the right one. Okay, if you need it, I've got some 470 K ohm resistors, which is a little more than the 27 to 100, but that's okay. It just gives you a longer charge cycle. Anybody need a resistor?
Now, you said the capacitor should be at least...
Yeah, at least, if you can, at least 100 microfarad, which I think wouldn't that one? That's 1,000, that'll work. If it's 1,000 or if it's 10,000, that's fine. The bigger the better, really. There's a 1K resistor if you need it. Anybody else need a little resistor? Actually, I think these are 470K, but that's okay. Need a resistor. Resistors, cheap.
Thank you.
Anybody need a resistor?
We do. Thank you.
So this is 100 microfarads, 450 volts. That's okay
Right,
to use
right.
with a
You
9?
can use, yeah, you can use it with 9 volts. Yeah, it's way under it, so it's fine. But you wouldn't want to put 500 volts on it. 500 volts would probably let the smoke out. Meaning it would go poof. Yeah,
As long as we're underpowering it.
yeah. Need a big resistor. It's this is a that's actually 470K,
Okay.
which would be even better. Okay, I'm sorry. We're not going to use the switch. Okay, just go ahead and hook everything up. Leave the positive side of the battery disconnected until you're ready. When you're ready, measure across the capacitor first, and it should read almost nothing with your voltmeter on DC. Okay, then plug in the positive lead on the battery while you hold and you may have to get your partner or somebody next to you to hold the voltmeter on there while you're doing that. It may take 2 hands or 4 hands. But anyway, what the idea is, when you apply the power to it, you should suddenly see that 0 volts across the capacitor start to rise, and it should rise up to about 6 volts or so, close to 6 volts, and then it'll go real slow after that, going all the way up to 9 volts. But you'll actually see that charge cycle. That's why we're using a fairly high value resistor to slow that charge down, and a fairly large capacitor because it takes longer to charge. The idea is to be able to see the charge and discharge cycle. Now, once we've done that, once it's charged, keep your meter on the capacitor, pull the positive lead, and watch the charge dissipate, go down across the capacitor as the capacitor discharges. Okay, now let's make. Some of you guys have done this kind of stuff before. Help me out. Here we go.
That's not, the positive is not in. Here's my resistor.
Okay, well you are hooked up here already.
Yeah, but I'm not hooked up here.
Oh, I'm sorry. You're right. That's fine. Okay. Okay, so we want to go then from. Let's move this one over one. And plug that one in right there.
Ah, gotcha.
And
they're
into
the
the
same
minus over here.
Take him over to the
And that
negative.
same 5, and then over to the negative.
And all of these are fine.
Any one of the whole row is fine. You got it.
Remember that. There we go.
Okay, now take your meter and measure across the capacitor. What value is your capacitor?
I don't know, I think it's pretty high.
Okay.
How do I do this?
Just go to DC volts.
DC volts.
There we go.
Measure across the capacitor from here. Doesn't matter, negative or positive.
On this meter, it doesn't matter. It'll automatically adjust. Okay, so it's basic.
Indecisive.
Are you on there good?
I was. Here. Let's go up here into one of those. 8.4.
Okay, now watch it.
Okay. Wow.
See, it's going up. It's charging. If we were really technical, we'd be timing it a little bit to see how long it takes it to get up to
How do we
about
know
6.
when it's out?
We wanted to get up to about 6 volts. Now, when I take that off, now watch it go down.
Wow.
And it's discharging now.
Yeah, sure enough.
Doing self-discharge.
So what's the resistor doing? Anything?
Right now, it's not doing anything.
Okay.
Now, what we could do, if we jumper this over to here, so that the resistors across it, we'd see it would decrease real rapidly.
Hook that up to the positive as well.
Just we
And
put
leave it
it
in the
across
same
it.
line.
If we
Gotcha.
put it across it, that way it discharges through that.
And that'll happen rapidly.
Okay, now don't do it yet. We got to charge it again first.
Okay. Let's charge it. Over to the negative.
Am I in there?
Boom.
Are we in?
All right. Now those are touching. Does that matter? It doesn't matter. They're hooked up electronically
They're
anyway.
the same one. Yeah.
It's going the wrong way.
No, it's fine. We just change the leads. This meter will automatically tell you if you have negative, negative, or positive, positive. That's all it's doing. Okay, so we take this off. We're starting to discharge, but if I whip this guy around here real fast and do that, it'll go down much, much faster.
Yeah,
So
you
that's the
crushed
idea.
it.
Uh-huh.
Nice.
That's the idea, and it's still disconnected.
And why would we do that?
Okay, we're fixing to talk about that. Okay, were you able to get some idea of what we're doing there? See the charge go up on the capacitor, then when you remove the battery, it'll gradually self-discharge. If we took this resistor here and moved it down to here across the capacitor, that would make it discharge much, much more rapidly. Okay? Need a meter? Yeah, just pick one you like. It's chilly. It's cold. It's cool. Does it work?
Yeah, looks
You
like
got power? Okay. Okay, now then, get your pencil out or your calculator or whatever you like to use. Get the value of your resistor, the value of your capacitor, and see what kind of time should it take to charge that capacitor. Doing the RC time constant.
What did you say my resistor was that you handed me?
470K. Those resistors that I handed out were 470K. Whoops.
I've absolutely no clue how to use a breadboard.
Okay, not a problem, we can fix you up. Okay, this row of pins are all connected together.
Okay.
But they're not connected to anything else. This row of pins are all connected together, but they're not connected to anything else. Each row of 5 are connected to each other here, but they're not connected to any other rows. Okay, so if we did want something like this, for example, we call this a power bus. So we have our negative voltage on that one, positive voltage all the way up on that one. So we want to charge up our capacitor. So let's just say we take this one here. What is that one? 180 microfarads, okay? So I'm going to hook the negative to negative. And I'm just going to pick a point to plug it in there to make it convenient. Make it easy to get to. And then we're going to take that resistor, and we want to connect this resistor between here and the positive leg. So to do that, we just plug him in. Right there, same in that row of 5 pins. All 5 of those are connected together. And then we hook this guy to there. I can put him in any one of that in that row because those are all hooked together.
That's all positive, and then
That's all negative. Now, if we measure across this cap right now on DC volts,
And we're doing.
go to DC volts.
This one. That's AC.
Okay, is that doing AC volts or, okay, I think we have to select DC volts. There we go. Okay, and then just put it across that capacitor right there and see what you get.
Yeah, I've got negative, but this is called gray. The blue line is, yeah, plus, so negative.
3 point.
Here, let me show you a little tip here. You take this guy, and just kind of stick it down in the hole right there with it.
Oh.
That way you can push down hard on it.
And do the
And
same
it'll give
thing
you,
here?
yeah, do the same thing there.
Okay.
Okay. So we're about 3.8, 3.9. We're still charging. Voltage is still going up. Okay. And if we disconnect it, can you pull on that connector for me right there?
Which one?
This one. I tell you what, I'll hold this and you unplug it. Just, there we go. Okay, now it's going to start self-discharging, dissipating the charge that we had on that 3.7 volts is just going away. Now, if we took this and suddenly moved it over to here, where the resistor is across these two leads, then this will discharge much more rapidly. But the idea is this resistor doesn't let this charge up immediately. It charges up real slow as it goes up. So let's put it on there again and we'll watch it happen. Okay, we're not quite discharged yet, so we need to discharge that guy.
All right, so
I'm going to cheat here just a second. So I'm going to take it loose from here and go to here right across that capacitor. Okay, so this resistor's across it, so it's going to make the voltage go down much faster. Well, not much faster, but it's going down, you'll notice. Slowly discharging. So I'm going to take that back out again. I'll just lay it aside and just take a lead here of any kind. Just short it out and see if we can get him to discharge there. Okay, now we're discharged. Okay, now we're going to do the charge cycle again. Put that one in there. We're not going to put that one in yet. Okay, so we're going through here, and we're eventually going to plug this one in there.
there, good. All right.
Okay. So power, as we said, power is going through here, through the capacitor, through there to there, through the resistor, back to here, and back to the battery positive. So I'm going to monitor this for you here by doing this. Okay, what do we got? 7 millivolts. Okay, hook our battery connector. Oh, wait a minute. We've got to plug this in first. Get in there, sucker. There it goes. Being a little contrary. Okay, now watch what happens when you plug the battery on. See, it's charging up very slowly, but it's coming up. 1.4. So got a large value capacitor and a large value resistor. It's going to charge relatively slowly, which is what we'd expect to see.
Okay.
And so we just keep, now if we were timing it with a stopwatch, we would be looking for about 6 volts to show up on here to consider it fully charged. But as you can see, it's going to take it a while.
Yeah.
Okay, so now let's calculate what should the time be. So let's see, this was a 180.
So what were you reading off of that? What is it?
180 microfarads
yeah.
times 470,000. So 180 microfarad would be 0.00180. So that times 470,000. And that'll give us the time in seconds that it should take it. Okay. Is that right? Yeah, that's probably right. 840, because it was coming up very slow.
846 seconds, right?
Uh-huh.
So if I divide that by 60, that'll give me, what, 14 minutes?
Yeah, to actually charge it up. Now, if we put a smaller resistor, that time would come way down. Or if we used a much larger value capacitor like this thing, the time would go way up again.
Right.
Okay?
Right. So when you were using a breadboard, and you've got a power source with the black and red, so
Correct.
I mean, does it matter? I mean, because I could flip this around, so it doesn't really matter black and the red.
As long as you keep it straight, it doesn't matter at all.
And then when we put the capacitor in, we took the negative lead or black lead and put it in the same
And to the black or negative, correct,
because
exactly.
that row's going to be black.
All negative.
That row's going to be all
All
positive.
positive, correct.
And then we go capacity to a row, and then we can put the the resistor in the same row to the
Correct.
positive.
Correct.
And then they're all,
Correct.
then, because then that keeps the circuit going all the way through.
Exactly. And if we want to hook something else to this same row, put another, plug into another one of the
could do a
holes
jumper
there
there.
and take it to wherever it needed to go.
Because we could do a jumper from one row to another.
Exactly.
And then it
Yeah.
activates.
Yep, exactly. If you had something where you need more than 5 connections, then you just take the jump from this one, say over to that one, that gives you 4 more. So you'd have nine places, or 8 places, I guess, to hook up at that point. Have 4 on either side. And you can daisy chain them as many as you need.
Okay.
Make them go.
So how do you connect it, like one breadboard to another breadboard? Just another
Same way.
jumper?
Yeah,
Same
if
thing?
we had another one sticking up here, we wanted, we just put a jumper from here up to this one, jump here to that one, and then that negative would go all the way up to here.
Because if you do it from these, it's gonna jump the power source.
Exactly.
To the
And I've got some pre-made jumper leads that are made just for doing that kind of stuff.
Oh, yeah?
Which we
Okay.
use in this. Okay, gang, how we doing? Did we figure out what's going on? Did you figure your time constant? We just figured his time constant. What was that in 14 minutes? 14 minutes to charge it up because he had a very large resistor and a very large capacitor. And so it's going to take, and we watched it on the meter and the voltage is creeping up because it's so large. If we had a smaller capacitor or a smaller resistor, that would go up much faster. Likewise, as I said, if we took that resistor here and moved it down to here, that would make the discharge much more rapid. So we play with the time constants to check the charge and the discharge. Are we okay with that? If you're not, I understand. My challenge really still is, get you a breadboard, buy you a package of mixed components, and try this. Do it on your own. I mean, you've got the notes on how to do it. So you can do this on your own. Okay, let's move on and talk about this just a little bit further. What's a practical application for this time constant thing? Okay, this particular thing is using what we call a triple nickel IC, or 555 IC, integrated circuit. The 555 timer circuit is made just for timing things. It'll do all kinds of crazy stuff. But what controls its discharge time is this resistor right here and this capacitor right there. Remember we said the time constant is resistance times capacitance? So I take that resistor, which in this case is a 100 ohm resistor, it got clipped off. A 100 ohm resistor and a 0.1 microfarad capacitor, multiply that, tells me the time constant. The IC itself then will monitor that. And at this point, it's monitoring the charge rate of the capacitor. It says, okay, the capacitor charges up to a certain rate, good. And then the IC itself will cause a discharge. And it'll repeat over and over. And we put 2 LEDs on the output over here, and so we'll blink the LEDs back and forth at about a 1 second rate. But the blink rate of these 2 LEDs is controlled by these 2 values on that IC. That's a very practical application. Now, again, if you come back and we do the triple nickel class, we actually have a class using that same IC where we actually build one of these up on the breadboard and actually do that and play with it with a triple nickel. It's a lot of fun to do that. So maybe we'll get to do that one. Okay. Inductors, changing horses a little bit. What's an inductor? It's a coil of wire, basically. That's what it boils down to. Now, let me just throw a quick side trip on you here. One of the little gotchas to watch out for is resistors. Resistors can be made up of a lot of different materials. Most common one is carbon. The resistance in a carbon resistor is controlled by how densely the carbon is packed. The more densely, the less resistance. That's the idea behind it. Those resistances, they were pure resistance. There's no inductance, there's no magnetic reaction in that whatsoever. But you can get instead a wire wound resistor. A resistor made with special wire wound around some kind of a ceramic core. Those are just a coil of wire, so they're also an inductor if you get a wire wound resistor. So if you're working on a circuit, if you look at something and you say, oh, this is burned out, this resistor is burned out, you need to be sure that you get a carbon resistor or a wire wound, whichever the circuit calls for, so that it doesn't mess up the tuning of what you're working with. Just quick side trip. What does an inductor do? Basically, an inductor, like a capacitor, stores a charge. The difference is the capacitor stores the charge on those two plates separated by an insulator. It's an electrostatic charge applied by the battery. The inductor, on the other hand, is a coil of wire. It stores the charge by creating a magnetic field. When you first apply the power to the inductor, creates a magnetic field, and the magnetic field just sits there. When you disconnect the battery, the magnetic field collapses on itself and generates a certain amount of voltage within that inductor. So the inductor charges up with a magnetic field. It sits static until you take the charge away, and then boom, it collapses and goes back the other way. Just like the capacitor charges up on the plates, sits there till you put something to discharge it, and the capacitance charge is dissipated through whatever that is that's discharging. Okay, just a coil of wire. Inductors are measured in henries, and henries is big. It's kind of like farads. So most of the things we'll see will be a micro henry or a milli henry, thousandth of a henry. And we sometimes call them chokes instead of inductors. It's easier to say. But anyway, you'll see that. You'll see either one of those terms used. Measured in henries or fractions thereof. Okay, the AC resistance in an inductor is called inductive reactance. The AC resistance to a capacitor, I failed to say that, is called capacitive reactance. So we measure it in ohms just like we would in pure resistance. But since it can vary with the AC and with the frequency and the values and all that, we don't call it just resistance, we call it reactance because it reacts to the frequencies that are involved. We say that an inductor will block AC but pass DC, meaning it's just a coil of wire and DC will just pass right straight on through and charge it up with a magnetic field and just sit there and go forever. However, if you're doing AC, it will tend to resist the AC because it takes a while to charge up and discharge. Where the capacitor will let the AC go right through, but it will block the DC, won't let the DC pass through. Reactance is measured in ohms, whether it's inductive reactance or capacitive reactance, it's still called ohms. Why do we care? Well, antennas is probably one of the biggest places that we see that as amateurs. When we measure our SWR on the antenna, we have true resistance, the resistance of the wire, the elements, whatever. And then we have the capacitive part and the inductive part. A lot of the antennas have a coil of wire on the bottom to make it look like it's longer than it really is. That's an inductor. So we have inductive reactance involved. A lot of antennas will add a capacitor to tune out some of that or nullify some of that. So we have inductance and capacitance involved. Both reactances involved. The idea then is to get in an antenna is to get resonance, which means the two reactances cancel each other out. The inductive reactance is equal to capacitive reactance, so they cancel. All that's left is pure resistance, which we want to be 50 ohms in an antenna in most cases. Transformers, one of the biggest places this is used. We talked about that earlier in AC. Transformer is just a big coil of wire around some kind of a steel or iron core. It has a winding, we charge up the winding, if the field collapses, have another winding over there that senses that. Depending on the turns ratio, on how many turns of wire we put on this thing, we can jack up the voltage, we can lower the voltage. They're inversely proportional. If we raise the voltage, the current drops. If we lower the voltage, the current raises. They go back and forth. That's just the nature of that. We still use the time constant, still works the same way as it always did, except we divide for this one. Inductance divided by resistance, where capacitance we multiply. So watch out for that little distance there. But we can do the same thing we did with the capacitor. We can add a resistor to it, and now we get a time constant. We know that we can calculate that with a certain value of resistance, a certain value of inductance. How long will it take for that inductor to reach 63% of the applied voltage? And so we can use that. Now, we really get sophisticated. We put an inductor, a capacitor, and a resistor in there. Then we can really start fine-tuning the thing and make it do some real work. So this is the same circuit that we're not going to build this one up because our time is just getting away from us, but you get the idea here. The same thing we did before. Now, generally speaking, these time constants are going to be much shorter than with the capacitor, so we wouldn't be able to see that much of a change in the inductor, but the idea is the same. And we can calculate the time constant with division. We're not going to talk about that a lot. Now, let's talk about inductors in general. And I have a package now labeled miscellaneous inductors. Random resistors, wrong one. And I hope that. Miscellaneous inductors, there we go. Here we go. Take a couple. Here you go. It's passing around, take a couple. You also have a color chart for inductors. The colors are essentially the same as for resistors or capacitors, i.e. brown is 1, black is 0, red is 2, etc. But these are a little bit easier to read generally than the capacitors are. Capacitors can be so tacky. There's so many different standards for capacitors. So anyway, everybody take a couple of those, and we're going to look at them and see if we can read the values, and then we'll try to put it on the LC meter and see what it says the values are.
Why is everything so tiny?
Yes.
Is a balun or an unknown a form of a transformer?
Yes, it is. The question is a balun or a form of transformer? It is a transformer. Basically, you have a toroid, which is just an iron ring with windings on one side, windings on the other side. So if you had 10 windings on one side, 10 windings on the other, you generally have an unbalanced, straight across, 1 to 1. And then if you needed a 49 to 1, we would adjust the turns ratio to give that particular impedance on either side. So it's used for matching for antennas, yes. They're just transformers. Okay, now, one little quirk. If you notice that inductor color code page that you have, there's one specifically for inductors. The military standard is a little weird. The military inductor starts out with a silver band, but then the last band is often also silver, so you got a silver band on either end, and you're like, now what do I do? Well, you get the instrument out and you measure it. That's what you do. That's what I do anyway. So anyway, just kind of take a look at those and see if you can read what they are. And then when you get through looking at it, so pass the meters around so you can measure those things and see what you think. Now, if you want to compare what the instrument shows you with what it says on the colors, you can do that. And then if the meter is way off in left field, we can get my little more correct meter up here that works a lot more accurately and measure with this little guy. And this will give you a pretty good reading on it. This thing's pretty accurate.
Are these polarized too?
These are not polarized, no. Inductors are not polarized.
I don't know, I put it on ohms, just so they determine That figures.
You probably don't have an inductance reading on
I'll have
that.
to come over here to Ron.
Yep,
now.
you're gonna have to pay you.
2 millihenries, and this is in microhenries.
Yeah, then it may not have enough range. I'll get Robert's using the other meter there. That's one of them. That's the military one.
This category here.
Yep. So, but the problem is it's got a silver on each end. So does it go that way or does it go that way? Now, in this case, the black, what's the value of black?
Black says
0. So we're not going to start off with 0. Okay, so we turn it the other way around. But we do have a red,
Okay.
which is 2.
Yeah.
2, and a 0. No zeros. So 20 should be 22 millihenries. Should be. Don't promise it is. Should be.
Okay. Millihenry.
Is that crazy or what?
Great asset.
It's practice. What do you think, crew?
So is it just a coincidence that mine is exactly, seems to be that? So we're saying blue is the first digit, is that right?
Okay,
And how do you
okay.
know?
How do you know which way to orient it first?
Okay, on these guys, generally the gold, silver, or
At the bottom?
black is going to be at the bottom, if you please, yeah, or to the right.
So that looks like blue, but I can't tell. These two seem to be the same color to me. You just have to have really good eyesight. Is that blue or, I mean, gold or gray, those two?
I think that is a blue, gray, and either an orange or a red with a silver band at the end indicating 10%
Oh,
tolerance.
red, okay, I wouldn't call that.
I'd say that's probably a blue,
So six,
blue, gray, and either red or yellow.
this is gray, so 6, 8. Okay, and then
So
red or yellow,
68,
so either
68.
times 100 times 1,000. And then what do I do with the tolerance?
That's the
plus
tolerance,
or minus,
how
so
close.
that's- it can go-
It's silver, so it's plus or minus 10%.
So, and so can this meter measure that?
Well, let's find out.
It looks like it can.
So it's L, right, so it's got a,
And how did you know which end to put where?
It doesn't matter on these,
These aren't
they're not,
color.
they don't care. Okay, and then we're gonna go to Henry's, we're gonna go to the top and work backward.
it's got something.
6, 8.
2
There's
millihenries,
the
we're
6
getting there.
we were looking for.
Okay, that's as far down as it'll go, is 2 millihenries. So that's saying it's 6 millihenries, that's as close as it can get.
Okay, so, but that was the first significant digit that we had was 6.
Okay.
So we think
Yeah.
that's correct?
So that's,
That's what's all we're
and
looking
again,
to do to measure.
these little cheapy instruments generally are way off on way off.
Measure it a lot closer?
Better.
Not that little instrument will measure, we can get it really close. You'll be very happy.
Yeah, let's go at one from the
Robert, can we use that little guy for a minute? One here, do my little, yeah, we're good. Oh, was that a resistor?
Well, that was the interesting thing, because this one read inductance.
Right,
When I
but
did
it may say it's real low resistance. Usually give you low resistance, then you hit the scroll button, and it will give you the inductance.
That's what I, that's what
Yeah,
I saw.
I'll come back to you in just a
Okay,
second.
this one read resistance, that's what this one is.
It is a resistor, yep. Mhm.
The calculation.
Yep. Okay, let's put this little guy on it.
I think that's. I don't know. In like that?
You squeeze it,
A
Oh,
little hook goes on there.
there you go, like that. Okay, and then on this little guy, you just tap the on button.
oh, this
And
is
it
the
figures
fancy
It'll
one that
calibrate,
does
it'll
everything.
calibrate it, it calibrates itself.
We need to look at this thing.
And it'll check it, see what it is.
Analyzing.
Okay, it says at very low resistance, which is okay. I'm gonna scroll. It's got 2/10 of an ohm resistance, very low resistance, that's fine. But it's 7.2 microhenries.
Okay, so it's close. We thought it was maybe 6.
Well, it could be 6.8 plus or minus 10%.
Yeah,
So that
which
could
would,
be where
which
we
would
are.
fall in there.
This is really cool.
It is, this is a fabulous little instrument for
like
the price.
idiot-proof.
It almost is, yeah, it really is. It works really good.
Throw another one on there and see if we can figure out what it is. This one has readable colors on it.
Oh, they just keep getting smaller. So it just does everything. You're just like, do the thing.
Just
and it
tap the button, and it'll figure out if it's a capacitor, a resistor, or a coil. And,
L, C, and R, it reads on
okay, and
there.
that says it's 88.6 microhenries.
Okay, let's see if we can make that make sense and give the meter to somebody else.
Okay, perfect. Thank you so much.
How we doing, gang? Try that? You'll love it.
Just connected, there's no polarity.
No polarity on inductors, correct. Okay, you just hit the on button to start the test. It'll calibrate itself. And it'll check it out, and it'll tell you what it is. Okay, it says it has very low resistance, which is not unusual for inductors. So we tap the scroll button and go to the next reading. It has 0.2 or 2/10 of an ohm of resistance, DC resistance, and its value is 7.3 microhenries.
Okay.
Does that come out close to what the markings say?
I don't know, I didn't check the markings yet. I was checking with the other meter.
Okay, let's look at the markings real quick. Can you read the colors? Let me go run. See if you can figure out, it should come out pretty close. What do you think, doctor? What do you think, doctor? I don't know. You don't measure one of these? Can you read the values off of it? You got good eyesight.
Golly, it looks like.
It's hard to see if it's red or orange. Look like red, black, or orange, red, black, or orange, black, or something like that. So I'd say it's either 22 or 33 microhenries. And the silver band plus or minus 10%. That's my guess.
So I think, yeah, I just gotta get that, one UHF antenna.
Okay, and then just hit the on button. And it'll calibrate itself.
But I just have to do it.
And it'll tell you what it is. If it has a real low resistance, it'll tell you that first, but it doesn't. 31 microhenry. So that is a 33 microhenry choke.
Orange, black.
Uh-huh.
Cool.
So 3 and no multiplier.
Structure I can put to the fence.
So the brown means it's a resistor, and the green means it's an inductor. Is that what that means?
No. The actual numbers here are the same, whether it's a resistor, a capacitor, or an inductor. You just kind of have to know if it's a resistor or not. Now, fortunately, this little guy will tell you. He will tell you what it is. But just to look at it, you know, if I didn't tell you, if I didn't know this was a resistor, I probably wouldn't be able to tell you that. Now, I could probably guess at it. I look at that and say, okay, that's a 470K, so that's probably a resistor, because you wouldn't see a 470K. Wouldn't see a 470K inductor on that size. So that's the idea behind it. Okay. You get a chance to play with this little guy a little if you wanted to.
I didn't, but I'm okay.
You okay? You through? Okay, I had a good question just came up there. How do you tell if it's a resistor or an inductor? Because the colors are the same. I mean, you know, red is 2 and orange is 3 and yellow is 4. It doesn't matter. You can measure with an ohm meter, or like in the case of, we were talking about the resistor, that resistor is 470K ohms. You're not likely to see 470K or 470 millihenries, especially in a tiny inductor like that. It's just not that. Possible, yes, but likely, no, it's not likely at all. Okay? Okay, so anyway, the little, Robert's got the little one up here. If you want to play with it some more, you're welcome to do that here. We're going to move on for the moment. Time sure gets away in a hurry, doesn't it? Okay, so we played with those things a little bit. Probably realize that capacitors are a little bit of a turkey. The markings, especially those tiny little capacitors that don't have color bands on them, can really be interesting. And you need a magnifying glass. I totally agree. Okay, impedance. The resistance to the flow of AC, basically. Impedance is whatever that amount of resistance is to AC going through a circuit, which includes the DC resistance of a resistor, the impedance of a capacitor, and the impedance of an inductor if it has all three. You add all those together and you get the total resistance, which we call impedance. We still use the ohms as the term, but impedance is one of those can vary because AC varies, the frequency varies, the values vary, and everything has to be calculated to see what it's going to be. Combined resistance, inductive and capacitive reactances, all that will vary with the frequency. Resonance is when the inductive reactance is equal to the capacitive reactance, and they essentially cancel each other out. We most often see that with antennas again. But that can also be true in any kind of a circuit that we work with. Ohm's law. We talked about Ohm's law in the DC class, which is that you have that little color wheel chart there, I think. Can I borrow yours just a second, Jerry? The little thing right there. On this particular one, they use the letter V for voltage, where most places use the letter E for electromotive force for voltage. Fortunately, I is kind of standard. I is current or intensity. How much current's flowing through, how intense is the current. But you get the idea. And that little wheel will tell you by looking at, covering one pair of values, you can get the other one and calculate what it's going to be. If it's going to be, if you're looking for the current, if you're looking for the resistance, looking for the voltage, or you can get the power that's being dissipated by a DC circuit. That same wheel works in AC with impedance. Now, what is impedance again, though? Impedance is the combination of resistance from a resistor, inductance from a capacitor, and inductance from an inductor. All that together comes up with impedance. But the formula still works the same. The only difference is here, instead of using R for resistance, we use Z for impedance, which I think makes pretty good sense, right? So the same formula, works the same way in AC as it does in DC. Just those values are derived differently. Okay. Any questions on anything up to that point? I know we're kind of drinking from a fire hose for some of us and running kind of fast and doing crazy stuff. Again, the point behind, in my mind, the point behind this is to encourage you to get you a little breadboard and play with some of these little things. See what they do. Try it. If you just got a breadboard, some resistors, and a multimeter and a battery, you can do that. That gives you some ideas. Now, we're going to get a little bit more serious at this point and talk about an oscillator. And unfortunately, I don't have as many of these as I wish I did. And I couldn't find any quickly to buy. So I'm stuck with what I've got. That little thing, okay, is a 4 megahertz oscillator. Tiny little thing, right? Okay, got 4 pins sticking out of it. It's called a 14-pin dual inline chip or dip. Because if all the pins were there, like a normal IC would have, there would be 7 pins on either side. So they count these 1 through 7 on one side and 8 through 14 on the other. So watch out for that. At any rate, built into this thing is a little crystal. A crystal, when a voltage is applied to it, will oscillate at a certain frequency, and it's very, very accurate. So they take that little crystal, put it with some integrated circuitry, and come up with a little generating circuit that will give you out one of these pins a 4 megahertz square wave signal. It just works. It's wonderful. It's a great little thing. So we're going to build one of these. Now we're going to try to do two things with this. We're going to put the circuit on the breadboard, take it over the oscope, and we should see that 4 megahertz square wave come out of it. That's fine and good. But what if we don't want a square wave? We want a sine wave. We want a nice round curved sine wave. What do we do to make that happen? We can add a filter to it, which we'll do, and that'll wind us up for the day. So that's kind of the idea behind it. You're going to need one of these little modules. I think I have 12 of these, so we may have to kind of double up a little bit on those. You can share. Okay, that'll help if you can share. And so we need one of those. You need the breadboard, you need the little modulator. You already have 3 batteries in the little battery holder, which will give you the 4.5 volts of batteries. And then you need some jumper wires. We were talking about this just a moment ago. Man, we got jumper wires. We've got commercial jumper wires that look like that. Got the little things molded on the ends. Or if you want to be a purist, you can make your own. Just cut you off a piece of wire, strip the ends of it, and make your own. What do you want to do? So I got lots of wires up here you can use. You do what you want. That's what they look like, single. Okay, so we got jumper wires. I got a box full of them up here. You take whatever you need. I'd recommend that you get the shorter ones. Some of those are like this long. You know, that's kind of long for the when you that little bitty breadboard. So you get the little 4-inch ones. They're a little easier. So that's the idea behind that. Now, okay, now you should have a handout about that oscillator. I don't remember exactly what it's called. Something about a 4 megahertz oscillator. Shows pictures of how to wire it up and all that. This is one of those cases where you don't want to wire it up backward. If you hook the module up backward, it can blow it. So don't do that. Okay? That's why I showed the pictures there. If you have a doubt before you hook the power to it, let me take a look at it, or let Ron take a look at it with you. Okay, so that's what you're gonna need. That's how we're gonna, there's the little oscillator module, we got the battery hooked to it, and we have an output and a ground. We'll hook that to the O-scope and see what it looks like. That's the idea behind it. So let's get the modules hooked, handed out here.
Oh, you want me to hand those out? All right.
Please.
So is your picture up there working from the top to the bottom?
I don't remember. And that's the wrong oscillator model. That's the 1.2. I've got a few of those we can do. We don't want to do that. Melinda, I just stopped advancing. Go by the handout, which shows you where the pin 1 is. Pin 1 is where the little Motorola symbol is. Yeah, this particular one there is an 8-pin module. It's a little smaller one. We didn't hand that one out.
This is what we're building, right?
Yes.
I'm gonna get in the way.
Melinda, I can't make it go.
Can't make it go.
Do you have any idea what we need to do to make it go back and go back?
Just hit escape and see if that does it. Are you sure? It's the whole thing. No, I'm not.
Honey, come here.
Can we call Lance? Do we have a fire?
Oh, right there.
Oh, we're deployed.
It's right there. Is that the one?
Is that you?
There we go. Now we're working. Okay. There we're working. What is the alarm that's going on? Somebody got something making the beeping sound? Or is that coming from out here? It says they got a system trouble alarm out there on their main panel. So.
Probably froze out the air conditioner.
What I wanted to see was the separation.
Yeah, you said to get it right. Does that matter?
Because I want to be able to actually connect.
Okay, I've got a handful of jumpers, the short jumpers here. If you need jumpers, I'll give them to Jerry and she'll take care of them for you. Thank you, Jerry. Okay. If we need more, I've got plenty more. We can uncrate some more. Probably don't need to do that. Okay, if you need me to give you a hand plugging all those things up, I'll be more than happy to do that. Jerry's got them in her hand, or I'll give you some from right here. Oh. You give Jerry, Larry is looking for some. How many you need?
We got a couple.
I handed them out to everyone.
You got enough?
I gave everybody two.
Okay, I got plenty of jumpers. If you need another one or something, it's not a big deal. I'm gonna lay them right here on top of this little scope so they'll see them easy. So what do you think, Doctor?
I think I'm a long way from being a doctor.
Okay, you're good there.
That's good. So then I gotta run a jumper from the power rail to 14, which is going to be right here to pin 14. But how are we counting through these? So would it be?
Okay, let me see. Tell me that. I got somewhere it tells us that. 14, 17. I thought I had that label where it made more sense, but I guess I didn't. Just a minute, I gotta figure that out myself now. Which one is pin 14? Let's see. Ground, power goes in 7 to 14. 14, okay, 14 will be this one, this one right there. That'll be the power one,
Right in the corner?
Oh, you missed it, You're in the wrong row. Come back this way, one row.
It's gonna be power to power, but it's gonna be, I don't have, can I put it, oh, I guess I can. Does it go right up flush against the edge of it?
Yeah, that's fine. Oh, excuse me, let me get down here on my knee. Okay, let's do it that way. So we're gonna put the plus in over here, right?
Yeah.
Okay, and we're gonna put plus to pin 14, which we're doing right there. Yes, I hope that's right. And then go from pin 7 to ground, which pin 7. So that's 14. God, I should have done a better job of late on those things. Why didn't I do that? I don't know why I didn't do that. Gosh, that's frustrating. Okay, noted where pin 1 is where the little Motorola is. That's what I believe. It's the very top, no wonder I couldn't see it. So we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. That's where I screwed up. I did say it, but I just didn't say it very well. Let's take that back out. Okay, so the pin 1, I believe, is the output. So 14, let's go ahead and get that one out of the way. So pin 1 is where the Motorola is, 1 through 7, 8 through 14. So 14 is going to be that one right there.
This one down here at the bottom?
Okay, and 14 is going to go to the plus power.
Oh, it's gonna go to the plus power, so that's gonna be the plus power over here, right?
Well, if you want plus over here, we'll just move this one over here.
Yeah, we just move it right there.
There we go. Okay, and then ground goes on pin 7. So we got 1 through 7 over here, so it'll be that pin at the end there.
And it's 7 here.
This way, one
more.
right there. Got it.
Okay.
Okay, that'll give us power. Okay, we want a jumper for pin 8. We need another jumper, don't we? We need another jumper. Let's get another couple of jumpers. Some of those jumpers are just kind of make it easy to get to stuff. Notice the very first line on the handout that says pin 1 is where the little Motorola symbol is. That's where you count from. So you start with 1 there and go down that side, go 1 through 7. You've got the other side, 8 through 14. Okay, so we got power applied. Now we need to get our output from pin 8. Okay, so that was 1, 2, 3, 4, 5, 6, 7, 8 is right up here. So that's our output. And we got to have a ground. This was ground, wasn't it? So there's our outputs right there. Okay, that's it. Now we already put the batteries in. And we'll turn it off.
And that would go right there. And then this one goes right
There.
here.
Correct. Now, we'll take the thing over to the scope. Put ground on here, main probe on here, turn the power on, and we should get a 4 megahertz signal out of it.
As long as it doesn't blow up.
Hey, we're not gonna let the smoke out. I hope. Let's go see it. Grab that thing and just take it over and check it out. They got a building alarm of some kind going. Yeah.
Can you double check this one?
Okay. Okay, which side's gonna be your negative side?
Well, negative, positive.
This is the positive side. Okay. And let's see what we're doing there. Let me back you up one. I don't have these memorized, believe it or not. Okay, so pin 1 is right here. So we go 1, 2, 3, 4, 5, 6, 7. And then 8 picks up 8 through 14 here. So this is pin 14 here. So pin 14 goes to the plus, just like you got it. That's correct. And then 7 goes to ground. 1, 2, 3, 4, 5, 6, 7, which would be this one right. Right there, you got that going to ground. That's correct, okay? And then the output is on pin 8, for the signal out. Pin 8's the output, so we go 1, 2, 3, 4, 5, 6, 7, 8, which will be where you got the resistor, that's correct. And we're going from there to across the capacitor through the inductor and back out. And then the output signal from this will be right there. Let me do that with a different color. There, and this was ground. So our output will be right here. The power will be input into there from the little battery box. But you'll need to load the battery box and be sure the power switch is off before you hook it up. And then we'll take it over and hook it to the scope and see what happens. We get it to go, guys?
I don't know. I got a flat line. Oh, I didn't turn it on, did I?
We got something.
We got something.
Okay, now we got to get the darn thing to sync up. Oh, I'm terrible with getting these things to stabilize our trigger. Nope, not that trigger. Position. Slope. Not worry about level. Okay, channel 1 internal. We're not triggered on that thing. I don't know if being contrary on us, that's for sure. Tell you what, let's use this little guy because he's got auto and not mess with it. Okay, but it's working. That's the main thing. Okay. Auto.
Auto's always good.
Turn off the menu, and there we are. Got a lot of ringing on it, but it's there. It's doing exactly. This little ringing thing that's there, 3.9996
There it
megahertz.
is. Pretty close. I'll give you an A+ for that.
Okay, that's how it works.
I gotta take a picture of your working.
So that's the idea. Now, we could probably tune the probe and get rid of some of this ringing that's there and get a better picture. But more than likely, the actual circuit is doing some of that ringing itself. It needs to be filtered. This stuff going up and down here,
As opposed to a perfect just
as
line.
opposed to a perfect square.
Grab ours
Correct.
and let's see if we can, see if it's right.
That's how it's done. That's it. Okay, so let's turn you off. And then we're gonna put a filter on it when you get to that. So we're gonna take this,
Can I look
we're
and
gonna take
see?
this output out of here. We're gonna build a little filter circuit up here, come out of the filter, and we should, we'll see it made
We'll smooth it
into.
into a sine wave.
I'll help you with that. I'll help you with that.
can you approve ours design?
We
before
wanna make
do
sure we
anything?
got this. Here's what I don't understand, is this rail negative and negative, are those electrically connected?
They're not connected.
They're not connected.
They're
okay.
independent, they're totally
Okay.
independent.
So I don't wanna use this negative, I wanna use this negative.
Use either one, it doesn't matter.
Doesn't matter, okay.
Doesn't matter which one you
And then
use.
we just have a negative lead on the negative
Okay,
rail.
and I need to look at the, that's pin one, where's
Pin
the,
one.
cause I don't remember
Yeah,
what does it say?
here's the working one.
All right, that's okay, we got it right here. Pin 14, so we go 1 through 7, 8, 9 through 14, so pin 14 goes to plus rail power, that's good. Pin 7, which will be the bottom one right there, goes to ground, that's correct. And the output is on pin 8, which is the top one right there. So that's our output and that's our ground, that should work.
So we
Okay.
just need our
Put power into it.
So power, again, negative is negative, so we just, power's gonna go on this rail, is that right?
Correct.
On one,
And that one's gonna go right in there.
and that's because that's where the, yeah.
Okay, which means that I can get this 4.5 volts anywhere down this rail. Get that, the negative 4 anywhere down that rail. There's nothing on this one or nothing on this one.
Got it, okay,
Okay.
okay.
So now, so those leads were just to be able to hook the.
Right, make it easy
The
to go
equipment to it. That is what?
ground,
That is ground.
and then that's the main.
And this one is black, that's on pin 8.
Okay, we didn't do something right. Yeah, we did.
Doing something, but it doesn't look like the other one.
We don't have something right. Turn him off.
Unplug it.
Turn the power off.
It's right here.
Oh, I got it in my hand, never mind. Yeah, okay, we got something that's not right. Let's try again. Let's see see the paper again.
Here, let's turn that off.
It's
Yeah.
off.
Okay.
Is it? Because it still looks like it's registering.
Yeah, it's just got garbage picking up. Okay, so we pick pin 14, 1, 7, 14 goes to positive, that's correct. Pin 7, 1 through 7 goes there and goes to ground, and that
They're the
is
same row?
correct. And then the output is on pin 8, which is that one, which we're going to there. And the ground goes to ground. And there's nothing hooked onto the one that says Motorola.
Is this one not in quite all the way? They look like they're kind of wiggling. Maybe they're not connecting correctly.
This should work. Is anything on the next page that we said? That's when we start adding the other stuff to it. Hook it up, make it go. It should go.
We don't want to hurt your.
Yeah, we're not reading anywhere.
15 megahertz, they're not even close.
Tear it down and start again, I guess.
Of course, it's also possible that module's got a problem. It's also real easy to get off one. I think I see what it is. I think it's right. Let's try that. I don't know if that's right or not.
Oh, you think it was in row 2 instead of row 1? That could be. Well, then the
You
other
have to
side
watch
is
those.
probably on also.
Have to watch those crazy things.
Don't hurt yourself or
So
yourself.
that one would have to move down to 2.
Yeah, that would have to move. It's on
That,
row 2.
actually, I think that is correct. Though. That should be right. That should be the right row. There's only 4 pins. 1, 2, 3, 4. And that was in 4. That looks right.
Okay, well,
That looks correct.
all right. Well, we get there.
And pin 7. What do we got? Pin 7. Pin 7 is the, wait a minute. Oh, that's right, minus. Yeah, okay. I started, we got it backward. No, that's right. And that should be right.
From pin 8 to the signal output point. How do we know what the signal output point is? This one. Plug a jumper wire into the
Pin 8,
oscillator.
right.
Pin 8 is the
1, 2, 3,
signal
4, 5,
output.
6, 7, and then 8 is that pin right here.
Oh, okay. All right, so
Is
it
that
just
one.
needs to
So
get
that
off.
should be right.
All right.
But it is not doing it.
Oh, we got a bad module.
And that's entirely possible.
It doesn't matter which lead we hooked up to.
Because truthfully, I have not, I have not checked all these modules.
See this black?
It's getting a little something out of there, but it's nowhere near what it's
black
supposed
Black
to.
is going to negative.
Okay,
Yeah.
and the red is good.
And then pin 8 is the signal output, and that's
Right,
going to
it's
positive.
also ground.
Okay, well, okay. We'll let somebody else do it, yeah. Thank you so
Might
much.
might have to try another module and see if that's entirely possible if the module itself is bad. I've had those for a while too. They've been through a lot of classes. Somebody else got one ready to go? Okay, that's ground, I take it? And positive? Okay, hold that so it doesn't swell out. Got it. Okay. Ready? Okay, we're not getting something there, so let's back up just a minute. Let's go back to the output. Okay, we got our square wave. Okay, so the module itself is working. Put out 3.9996, which is close enough to 4 megahertz. So we're doing good there. And we come out of there and we got a capacitor going to ground. You can see it starting to, it's not making good connection, is it?
There we go. So essentially you're looking for that square wave in the path?
Well, this would be smoothed out, right? This would be
That's what
more
we're-
like a sine wave, because you get it's filtered, right?
Yeah, we've got an output here. Yeah, we got a good output. That's the output from the module itself. Whoops, I just lost it.
Oh, here you go.
Yeah, I pulled it out, that's why I messed it. But when we go into here, wait a minute. Hold the phone just a second. See, hold all that. Go ahead and turn it off if you can, just for a second. That's that 470K. Let's put a smaller resistor in there. Hang on just a second. Making headway, gang. Okay. Now then, let's take that one out and put this back in its place. Let's see here where we are. Okay, we're still on.
Turn it on now.
Okay. Okay, notice it's starting to wane. It's already starting to look more like a sine wave. That's the square, there's that one. Now let's put the little capacitor back right there where it was.
So everybody says you should turn off the power while working on circuitry.
Yeah, you really
Every
should.
electrician.
And that particular capacitor is taking all the signal out.
And no one ever does.
We need a smaller value capacitor there. It's basically sucking all the signal. That's okay. We get the idea. You see it's starting to round, and we get down to here on the end when it should be even rounder still.
Harmonics everywhere. The FCC was knocking on the door. What are you doing? I'm not doing anything.
Well, we're not doing good, are we? We're good there. Oh, that's a .01 also, that's probably why. Let's take that out. And then we're still getting, even just with the inductor, we were getting smooth pretty good, making it into the sine wave. These two values here need to be real small values, but one of those was a .01, which is way too much. And the other one was a 150, probably 15 microfarad, which is probably a little too much. So we use smaller values there. It would help smooth it, just to make it a little more round and a little less triangular. But that's the idea behind it. So looking good. It works. That's the main thing. Here you go. Anybody else got one you want to try?
Let's give it this shot.
Okie doke.
I haven't verified it yet, so power's off right now.
Okay. Power to 14 and negative power to, we missed a pin right there. Okay, let's move that down a little bit and give us a little more room there. There we go. And an output there, comes there, and goes through all the network and comes out there. Let's see if it works.
Turn on the power yet?
Not yet, not yet. Okay, and we're going to check it coming straight out. Okay, now turn her on. There it is. Okay, now we come out to here. Okay, you got the same problem. You got that 470K resistor. It's too big. It's all the signals getting sucked to ground with that capacitor on the outside. We need a smaller value there. Put up he had to get the resistor that he used for that.
Let me borrow your resistor.
So we've proven one that doesn't work. Well, Bob Warren at this point is so some of these
Right there.
are designed more expensive. They're like full for the first time. You can hook them up backwards.
There we go.
Whoa. That's interesting.
It's a 12 picofarad. Okay, so it's got a little too much capacitance there. It's sucking it to ground basically. But you can see it's starting to modify the waveform. When we come out to here.
This network is what we're calling a filter.
Right. We can see it's.
So how is this used to modulate voice or like how? I guess this is the beginning of a radio, right?
It could be. The frequency generating elements for it, yes. We'd come out with a digital circuit, which is going to get a square wave, but you need a rounded wave to feed the rest of the circuit. So you put it through a filter, round it out, and let it go on through the rest of the circuit. That's the idea behind it, yeah. We'd have to play with these two capacitor values there to get a better value. I'm sorry, I plugged in the wrong place anyway. That's not very smart. That makes sense if I hook it up in the right place. Okay, there we're still modifying quite a bit. We got it into a triangle, put the small right value cap back in there, and that would make it actually smooth up. It'd be pretty close to sine waves. Yeah. Not bad.
First official circuit, I guess.
It's a real thing. Ready? Okay, power into there. Ground into. Okay, we missed a pin right here. 1, 2, 3, 4. There we go. And there in the output, we're looking good. Okay, we can take ground from there. And the output from right here. Oops. Unplug. Can you plug me back in there? We're good. Okay, come on. Okay, well, we're getting nothing. Push the auto button on it for me, would you? Push the auto button. Okay, that's the actual output of it. I think. Yep, okay. Make sure it really is generating. It is. So we're already doing some modification on the wave even. I'd take that old capacitor out. It was taking it all to ground.
This one?
Yeah, I just took that one out. But anyway, you can see it's modified it considerably already coming out. If I take this one out, from there, we should have a square wave now. Wow. Whoops. I can say whoops, right? Only surgeons can't say whoops. Trying to come straight out. I should be getting a square wave out of there, not that. I think that module is sick. Yeah, that module, it should be giving us a nice square wave. Most of them do, but that one's not. So anyway, that's the idea behind it, and just unplugged. That's okay. We're going to take it down anyway. Got it? Okay. You bet. How we doing, gang?
Big ceramic insulators, you know.
What do you think, doctor?
What would be in it?
Yeah.
Because I can get us one.
Okay. I'm just trying to get, I think we now have
Sir.
scouts that we will have a bunch of scouts.
FYI.
Yep.
And I'm on,
A lot of overshoot.
I'm on 5 volts per division, and I'm running off 4.75 volts.
Karen, you filtered? No.
No, I just went
Straight out.
There wasn't enough output power to get through the
Through the filter. Yeah.
You know, I paralleled
Yeah,
the
you have to-
resistors.
you have
Still
to-
couldn't get anything through.
Yeah, you have to play with those values of capacitors too a little bit.
We didn't-
Some of them had they were such a basically the capacitor was just taking everything to ground.
But I wanted to show them it worked.
Yeah.
Right, but anyway, you know, we're
I'm not sure what's the
So the actual voltage, the real voltage, peak to peak, is,
about 7.
that doesn't make sense.
Do anything like that? No, I don't know that you will.
Oh, it's giving me ratio. Did I press ratio? How did I do that? I don't know what I'm doing.
Believe me, it's easy to do.
Well, anyway,
Got more voltage coming out than we got
10,
going in.
15, almost 20 volts peak
Yeah.
to peak. So it's interesting.
It doesn't have any load on it either.
No load.
Yeah.
No load.
Put a little load on it. Probably. That makes some.
I just want to show you.
Yeah.
This one worked. This one didn't work.
Yeah, I guess I got a couple modules that are bad.
Well, these guys tend to be very touchy. They're for production work.
Yeah.
You know, you put them in exactly the way it's supposed to. It's a pick and place, right? You
Yep.
know, it's not like hobby.
Like we're doing here.
Yeah, right. Thank you.
Okay, I laid the stinking clicker down somewhere. I have no clue where. The slide clicker. Okay, I laid down the slide clicker somewhere. Anybody see that little long thing there that advances? There we go. Thank you. I forgot where I left it laying. Okay. Anyway. But this was just the first slide. This says the same thing you have on the handout and where you hook everything up, and we check it out. And now, one of the problems we have that some of those modules are bad. Honestly, I should have checked all of them. I only checked a couple of them, and I didn't. So apparently a couple of them are bad. Like Ron said, those modules are really made for a much more precise operation than what we're running in here. But anyway, The output of it should normally be a nice square wave, or fairly nice. You may get a little bounce, a little bit of spiking out of it, but it'll be a square wave. So we want to make it into to modify that. We use an RC filter again, resistor capacitor, and a choke filter called a pi network, and it's called a pi because it looks like the symbol, mathematic symbol pi, as you can see where that and the little inductor in between there. And with those things, basically what those things do is they trim off those sharp edges of the square wave so that you wind up with a sine wave. And that was the idea. Somebody asked, well, why would we want to do that? Well, when we, in our radio, most of our radios are going to have a digital oscillator for the main oscillator to get everything started, and it's going to put out a square wave. But the other circuitry after that are going to want to see a sine wave, so it gets modified inside the radio to do the same thing. Now, all this stuff we're doing, they can put that in a little tiny microchips that's a tenth of an inch square, you know, where we've got it all spread out so we can see it. Okay, that was how we looked at it, and that was just some things we did, played with it. We've already done all that, I think. Okay, now then, what have we accomplished, if anything? Anybody got any idea what we've accomplished? Do you feel like you've accomplished anything? Maybe I really should ask that. You know, this is, as I've said, usually in the write-ups, these things are not trying to make you into an electrical engineer. Obviously, that's not the idea. The idea is to get your feet wet, more correctly, get your fingers wet, playing with some of this stuff, hopefully induce you to get your own little breadboard, go play with it. You learn, at least I do, I learn by doing. It's so much more important for me to do it than just to read about it. And this is an inexpensive way to really get in and see what's going on. Then when you look at that test, especially if you're upgrading to general or extra or whatever, they ask those crazy electronic questions. It's much more obvious why they ask those questions and what they mean. They actually mean something to you. So that's the idea behind it. Get in there. It's easy to just say, well, it's all in the package. I don't have to worry about anything. And that's true. You know, in the old days, whatever the old days were in quotation marks, where you could build your own equipment, then you really would use some of this stuff. Use the O-scope for tuning and all those kind of things to make it work. But today it's all in the package. But it's still nice to know what's going on inside the package. Okay, next time we'll talk solid state. We'll bring some diodes and some photocouplers and a few little things like that, and we'll actually make that happen. We'll also use the little transformers. We'll build a little rectifier power supply circuit to power the opto isolators and turn on some LEDs. And we'll talk about transistors and diodes and all those things, LEDs that go with that. And amplification, how amplification works, some things to watch out for. In the meantime, of course, we want you to have a good time and be thinking about somewhere along the way, if you want to do a project at the end, there's a lot of different things we can do. From a very simple thing where we just order a little prefab kit. You know, we got a little circuit board and a half dozen components, and we've got solder. One of our club members gave us a bunch of soldering irons, by the way. And you solder the components in there and build a little something, a little FM transmitter or a little thing that blinks the two lights, or the little LED Christmas tree, you know, has LEDs down and blinks the Christmas lights. There's all kinds of things. Those little kits run anywhere from about $5 to $25, depending on what's in it, how much is in there. And we talked about doing a soldering class anyway, and there's a couple of those are geared for soldering as well, as training for soldering. Okay, so anyway, that's kind of the idea. Any questions, any comments, anything at all?
And I won't retain any.
Thank you. You guys are very gracious. You're very gracious. Thank you. I realize there's some confusion as we're handing out parts and doing all these things, and swapping instruments and sharing instruments and all that, but hopefully you get something out of it you can use. Now, last line, if you have a question, feel free to text me or email me or whatever's convenient for you. I'll be more than happy to field anything comes up after the fact. Now, with that, if you would, help me clean up all the stuff. If you take the batteries out and just kind of stack things in piles there where we can pick them up again, that would be great. With that, it's 11:54. We're about on schedule. We're done. Thank you very much.